Great. Oh, yeah, let me turn on the laser pointer. Good. Yeah. So, welcome guys. Good evening. Welcome to the last problem solving session, the TA session for the course Analog IC Design, which is being conducted by Professor Sankaran Anirudhan from IIT Madras. Just to introduce myself for the last time again, I am Soham Lakote, currently a fifth year PhD scholar at IISc Bangalore, working under Professor Gaurav Banerjee in the area of FMCW radars for vital signs monitoring, which is a sub area of analog and RF circuits. So the session organization will be same, like we will first take a session for 55-60 minutes. We will see if we can take a break today and then we will resume our session. All the lectures are being uploaded to this particular YouTube channel and I hope you all are able to access these lectures. And in the description section, you will be able to find the link for the presentation folder where all the lecture notes are being uploaded. So this will be the organization for this session today. This will be the last session. So I have also posted yesterday on the community channel of our YouTube. So we will be covering the most important questions from the assignments because some people had some doubts related to assignments. So, and since you guys have exams day after tomorrow, I thought this is the best way I can utilize this particular session. Then towards the end, I would like to cover two additional topics. What are the few more courses that you need to do to become good analog design engineer? And the last one is about the interview topics. So for example, if you sit for the interviews, any companies like Texas Instrument, Qualcomm, MediaTek and all, to take a job of analog engineer, what kind of questions you should expect, what will they look in you, what will make you a suitable candidate for that particular position, how can you make your resume stronger, and what are the resources for which using which you can actually gain those skills. So this will be the organization. So the only difference that I will be making in, since there are many questions that we have to do, I have already written some formulas and I have already written the approach for the questions. So it is almost impossible to take questions from 8 assignment and solve them within within let's say 90 or 100 minutes. So what I have done is I have already written at least some part of the solution. I will also write if anyone has any doubt, but we will go through them and we will see if anyone has any particular doubt. So I will not be able to solve each and every question in live in front of you because of the time limitation, and that won't be an efficient way because I want to cover maximum number of questions here so that you guys become completely prepared before going to the exam. So that is the only format change that will be there for this particular lecture. Okay, so now let's start from the assignment 4. Why assignment number 4? Because in the first 3 assignments you have usually seen the questions related to the calculation of the phase margin and all, correct? But from the assignment 4 and assignment 5 as well, you have a good questions which asks you to calculate the phase margin and to design an amplifier to get a particular amount of phase margin, correct? So it doesn't make sense to take the phase margin questions separately. So that's why I have started with the assignment number 4. So now let's look at this particular question. So just by looking at it, you should be able to think that, okay, this is the first stage of the amplifier. This is the second stage of the amplifier. I'm able to see some kind of capacitor which must have been used for doing some kind of compensation to improve the stability, correct? To improve the phase margin of the amplifier. Now when I take this amplifier, correct, and put it in this kind of unity gain feedback, this is the final circuit for which I have to design this amplifier. This application will determine what kind of spec should be there on the circuit, correct? So but this is not a design problem. They have given us the GM G0 values. So what you can see is that these individual stages will be of course made by transistor level circuits, but for this particular question, this is they have not given any kind of transistor design, correct? So now these are the values they have given. So now I will just ask you a few questions. So where do you think the dominant pole of this circuit will lie? Just look at the figure 1 first and just tell me, where will the dominant pole of the circuit will lie? At which particular node? Here or here?
Output of first stage.
Output of first stage, very good. And why did you say that? What will happen to this capacitor when it comes here?
So the Miller capacitor value will be like higher in the first
Yes,
stage.
excellent, very good. So basically what he's saying is the gain of the second stage is there, right? So from Miller multiplication we know that 1 plus AV times whatever capacitor is there between these two particular points. So whatever gain is there between point number A and B, this is what I have written over here, correct? So this is actually the gain of the second stage over here, correct? So what this guy is saying is, so if I just look at this particular figure, the capacitance that will be presented at node A will look something like this: Gm2 by G naught times C. Correct? So this is a kind of capacitor that I will see at point A, from point A to the ground. Correct? Now this is okay, that is really good. And so now whatever R and C will be there at point A, they will form a dominant pole. Correct? From where will I get the R? Remember, this G naught is nothing but 1 upon R naught. Correct? Of the first stage. So there you have a resistor, then you got this particular capacitor. Now since the value of this capacitor is so huge because it is getting multiplied by the gain of the second stage, the pole at this particular node will be at a lower frequency. This is what we usually expect. Now one more question, what do you guys think, whether there will be any zero in this circuit or not?
Yes, sir, because there is the parallel path from
Yes.
C and
Excellent, very good. So you guys are now completely familiar. Whatever current will be there from this path, and there will be a current that will be going out or coming in from this at the output of, that is at point number B. Correct? So these two currents can sum up at a particular frequency and yield a zero value. Correct? So that is why we have a zero over here. So now let's see what questions these guys are asking. So the first thing they are asking is determine the magnitude of the overall DC transconductance of the two-stage op-amp. Correct? So the overall transconductance means the GM of the circuit. We have seen this 100 times. Correct? So the GM of the circuit is nothing but I out divided by VI. Correct? So now we have to see what is the current. Correct? And they are just asking about two-stage op-amp. Two-stage op-amp means only this particular structure in figure 1, not anything in the figure 2. Okay, we are just talking about this particular circuit. So now if I want to calculate the output current, so what is actually going to happen, I will apply some input voltage. Correct? Some input voltage I will apply, correspondingly a current will be generated. So if I am applying this at a negative terminal, the direction of the current will look something like this. Correct? Now because of this, some voltage will be generated at this particular point. Correct? Let's say Vx. Correct? And now not Vx, let's say VO1, because this is the output of the first stage. Now when this voltage has been applied as the input to the second stage, again some current will be generated. Correct? Again some current will be generated, and the direction may be right or left. We have to see the signs accordingly. Correct? So now that current I out that I will be getting divided by this Vi, this is what they are asking us. Correct? So what I have done over here, I have just broken this into two stages. So first I am applying a Vi. This is the first stage. Correct? You have a R01 over here, and since I am applying the Vi at the negative terminal, over here what you can see is the direction of the current is going into the output point of the transconductor. Correct? So the voltage that will be generated will be negative. Correct? It will be negative. So this is what I have represented like this. Correct? So the output voltage will be nothing but this particular current. The value of the current will be what? Gm times Vi. This current when flown through the R01 will generate this particular voltage. Correct? And now when this voltage, if I apply this VO1 voltage over here at the input of the second stage, what is going to happen? The GM2 times VO1 current will be flowing at the output. Correct? And now that GM2 times VO1, this is what my output current is. Correct? So if I represent VO1 in terms of VI, correct? Now why am I doing that? Because remember, I want a ratio of I out by VI. Correct? The moment I do that, I will get the expression for the capital GM. So if you substitute this equation in this particular equation, correct, what you are going to get is, it will look something like this: the GM2 times GM1 RO1 by VI into VI. Correct? So the VI will get cancelled, and your total transconductance, the capital GM of the circuit, will be nothing but GM2 into GM1 into RO1. Now let's check dimensionality. Correct? So what is this? This is the dimension of the GM. Correct? It is nothing but 1 upon ohms. You can say this is also 1 upon ohms, and the dimension of R will be ohms. So this ohm and this 1 upon ohm will get cancelled, and the total dimension is 1 upon ohm, which makes sense because we are calculating the capital GM of the circuit. What you have to do is you have to just put these values over here and you will get the answer. Correct? So I won't be solving all the questions in a numerically intensive manner because we have to cover a lot of questions. I will just make sure that I will at least give you an approach. If you really want to do a numerically intensive calculation, then the main T of the course has already uploaded the solutions. Correct? So you can follow this approach, use the solution that the T has uploaded, you will get the final answer very easily. Correct? The numerical answer I am talking about. Okay? Now once this is done, let's look at the second question that they are asking. Now we have calculated the transconductance, the capital GM of the circuit. Now they are asking us to determine the overall DC loop gain of the circuit that is there in the figure 2. So the difference between figure 1 and figure 2 is basically we have some loading element in the figure 2 that is not present at the figure 1. Correct? Now what do you think, what should come in your mind when this DC loop gain term comes into your picture? You can see a feedback over here. What should I do over here to calculate the loop gain?
Break a point and see what comes written.
Exactly. And what point you usually break? Generally we try to break the loop at a point where we are going to see a high impedance, correct? So impedance looking at this particular node is extremely high, almost close to infinity at DC, correct? So that is why we are breaking the loop at this particular point. Then we will apply a test voltage over here, and now we will see what thing comes back over here, correct? This is what we are going to see. So now let's try to see, and let's try to combine these two. Let's try to combine these two in this particular diagram over here. Correct? So what I have done, if I break the loop over here, I am applying the V-test at the negative terminal. Correct? I am applying the V-test at the negative terminal of the op-amp. Correct? Negative terminal of the op-amp and the terminal of the first transconductor, they are having opposite signs. Correct? Just remember this. So now I am applying it at the negative terminal. My only job is to see how much output I am getting if I apply this kind of V-test source over here. Correct? This is going to be very easy. The gain of the first stage GM by GO1, correct? Everybody knows that. The gain of the second stage would have been GM2 by GO2 if there was no loading at all. Correct? What happened to the output capacitor? They asked me to calculate the loop gain at DC. So I open circuited each and every capacitor that is present in the circuit. Correct? So this would have been GM2 by GO2 if there was no loading. Correct? But since I have a GL element that is present over here, this GL and this G0 will come in, what you can say, this RO is there and this RL will come in parallel with this, correct? So if I look at in terms of the transconductance, it will be nothing but GO plus GL, correct? So that is why this gain of the second stage is modified to GM2 by GO2 plus GL. So this is the gain that we can easily calculate. The GL value you can easily find out because 125 kilo ohms has been given to you. Each and everything GM and GO of both the stages have already been given to you. So this you can very easily find out. Correct? Now the next question comes up is to find out and determine the value of the unity gain frequency. Correct? Now we have to take into account this capacitor. Correct? Because remember, the reason why we have this capacitor is to stabilize the system. Correct? What do I mean by that? So around the unity gain frequency, your system should act like a first order system. Correct? Your system should act like a first order system. So after the unity gain frequency, whatever extra poles you may need to have, you can have that. But before unity gain, I just want one pole. Correct? I just want one pole in my system. And to do that, we have inserted this C over here. Correct? Now our job is to, of course, since we are talking about the loop gain, we have to talk about the circuit where we are breaking the loop. And now they are also asking us to calculate the unity gain frequency. Correct? So everybody knows that this unity gain frequency will come out to be something like GM1 by C. Okay, but let's just, for the sake of everyone, let's do a small derivation of this. Correct? So that, because I will need this in the further sums as well when we move to the next assignment. Correct? So now this is what I was talking about. Correct? Now omega UGB, if your system is acting like a first order system, correct, then you can easily say that your omega UGB will be nothing but A times omega P. Correct? What is the A? A is the nothing but the DC loop gain. We have already calculated this in the previous question, right? GM1 by GO1 for the first stage and GM2 by GO2 plus GL in for the second stage. Correct? So I already know the value of A. What about the omega P? Somebody has already said, like we have already seen how to calculate the dominant pole at this particular point over here. Correct? So now how to calculate the dominant pole? So remember, what is the gain of this second stage now? The gain of the second stage is this particular quantity over here, correct? GM2 upon GO2 plus GL. So now the gain, so what I was saying is the C, the compensation capacitor C will be multiplied by the gain of the second stage, and the gain of the second stage is nothing but this particular quantity, GM2 by GO2 plus GL. If there was no loading, then I would not have to take this GL into account, correct? But since the loading is there, I definitely have to take its effect into the account, correct? So that is why you can see that the net capacitor C has been multiplied by this particular quantity which I have already shown you, and the RO1. So the RO1 is nothing but 1 upon GO1, correct? Which is nothing but the output resistance, the net resistance present at this particular point over here. Correct? So this is how you can easily find the expression for the pole 1. Now we are interested in the unity gain bandwidth. So we have to multiply this expression. Correct? We have to multiply this expression, or basically a simplified version you can say as this. Correct? How did I simplify this? Because this particular quantity will be usually much greater than 1. So this one I have ignored over here. Correct? Now if you multiply your A, this expression, with this particular expression, you can easily see that this GO2 plus GL, this GO2 plus GL, they are gonna get cancelled. Even this GM2 gonna get cancelled. The GO1 and RO1 are also gonna get cancelled. So the final expression you will be having is GM1 by C. And this is what we had expected. We have seen this so many times in this course, that the unity gain bandwidth of a two-stage amplifier, assuming that it has been compensated properly, it will come out to be GM1 by C. Correct? This is what we have already seen. So now GM1 is already known to you. The C value they have already given in the question. You can easily find out the value of UGBW from here. Correct? The only thing is, please, after doing so much of hard work, please do not make mistakes in the units. The unit for this particular quantity will come out to be radians per second. If they are asking you to calculate in megahertz, then you have to divide this particular answer by the factor 2 pi. Please remember this, okay? I don't want you to make any mistakes and lose marks because of this. Correct? I hope this particular point is clear. So now, once this is done, now let's try this. Yeah.
Sir, how like we can say the omega UGB is the product of gain and the dominant pole? I'm not clear with that part alone.
Okay, so see, just remember, you have this particular gain over here, correct? You have this particular quantity. Now the thing is, unless you have to drop some gain, see by what quantity this particular term rolls off, 20 dB per decade. Right?
Yes,
and from where does this come? This comes from this particular quantity, A0 upon root of 1 plus omega by omega p the whole square. You agree with me? This is the magnitude.
Yes, sir.
Correct?
Yes, sir.
Now if I am operating if my omega is sufficiently greater than omega p, can I ignore this one over here? Right?
Yes, sir.
Can I ignore this one in the denominator? Because if omega is much greater than omega p, then this value is going to be much higher than 1 over here. Correct? So this particular term, what it will reduce to omega by omega p. So this will be nothing but A0 omega p by omega. Now this is the magnitude. This is how your gain is gonna roll off at a frequencies which are significantly higher than omega p. Correct? Now you are trying to find out when does this magnitude becomes equal to 1. Correct? When it becomes equal to 1, your omega will become omega UGB. Correct? This omega I am replacing with omega UGB now. Correct? So now just if I put this omega UGB on the right side, your A0 omega p will become equal to omega UGB. Is it clear?
Yes, sir. Understood, sir. Thank you.
Yeah, and always remember, you cannot use this expression for frequencies which are very close to omega p. Correct? This only holds true when omega by omega p is much greater than 1. If you try to use this over here, then the problem is there will be some error in your final answers. Correct? So you usually don't want to do that. At least in the exams, for the first cut design examples, you can definitely do that. Okay? Yeah, that was a good question. I hope everything is clear now. So by the way, what we will do is, after each and every assignment is done, I will take a break of 1 minute just to see if anybody has any doubt, so that we don't rush through this particular lecture. Okay? So now let's look at the question number 7. The position of the dominant pole, we have already seen. This is our expression. Every value has been given to you. You just have to put this in this particular equation. Correct? Dominant pole is done. What about the non-dominant 0? We have to see this 0 now. Correct? So now from how can we calculate the 0? Remember, there is one current flowing like this. There is one current that is flowing like this. Correct? So when the sum of these two currents become equal to 0 at this particular point, correct, what you can say is that your output will be 0, because remember, your final gain is nothing but GM times RO, and GM is nothing. GM comes from this current, the short circuit current that you find out. Correct? I out by VI. Correct? You don't want this particular quantity to become 0. Correct? For calculating the 0, you deliberately make this quantity equal to 0. Correct? So now what we have done is, basically we are seeing if there are two parallel paths and there is a frequency dependent phase shift between the two paths. So now I don't want to do the small signal analysis to find out the value of the 0. I can just write the expression of the current. At a frequency where 0 occurs, my output is 0. So I can short circuit it for that particular frequency. Correct. So the current flowing through this path is nothing but Vx upon 1 upon Sc. So this term I have written over here. Since I am applying Vx at a negative terminal, the current will be flowing through like this, and the value will be nothing but Gm2 times Vx. Correct. So sum of these two should be equal to 0 at a frequency, and that frequency which I obtain is nothing but the 0 for this circuit. We have already seen this expression. It comes out to be Gm of this circuit upon C. So this is a similar thing that we have got. The Gm2 is known to you, the value of C is known to you. You can easily find out the value of 0 from here. Correct. Now once this particular thing is clear, they are also asking us to calculate the position of the non-dominant pole. Now remember, when you are talking about the non-dominant pole, correct, you are talking about these frequencies. You are talking about frequencies which are greater than omega UGB. Correct. So this particular capacitor C is usually starts affecting from this particular point. Correct. Since the second pole is much greater than the first pole, this capacitor at that particular frequency will act as a short circuit. Correct. It will act as a short circuit. And now why am I telling you this? Because remember, to calculate the second pole, what you have to do is you have to find the net R and the net C that is present at this node. Why at this node? Because I know at this particular intermediate node, my dominant pole is gonna occur over there. So the only other node where I can see the combination of R and the combination of C is the output node over here. Correct? It is the output node that you can see at this particular point. Correct. And remember, we are doing this for the loop gain, so you have to take this factor into the account. Correct. So that is why I have loaded the amplifier with this particular load over here. Correct. So now the net R, if I want to see, there is one RL that I can see, and now there is one more circuit that I can see. So it is nothing but a diode connected kind of transconductor. What do I mean? The output and the input of the transconductor are shorted together. Correct. So now what is the impedance looking at this particular point? So if I apply a Vtest voltage, so how can you find out the impedance looking at any circuit? You usually apply a Vtest, correct? And you find out how much current is flowing. Correct? So this Vtest upon Itest will tell me the impedance. Now if I apply a Vtest over here, the same Vtest is going to come at this particular point. Correct? Now that Vtest will generate what? It is gonna generate a current of Gm2 times Vtest. And the same current is gonna flow through this particular voltage source as well, correct, in this particular direction, because remember the Vtest is coming at this negative terminal. So the total current that is flowing is basically Gm2 times Vtest. The voltage I have applied is Vtest. So if I divide both of them, then what you can see is nothing but the impedance is nothing but 1 by Gm2, correct. So the total resistance at this node will be nothing but 1 upon Gm2 times parallel RL, correct. But remember, this particular quantity is gonna dominate, correct, because this is very small compared to RL. RL is huge, correct. RL is going to be huge, correct. So the net resistance will be dominated by this 1 by Gm2 term. The net capacitance is just CL, so that is why the pole will be nothing but Gm2 by CL. Again you know CL, again you know Gm2, so you can easily find out the value of this non-dominant pole. The only thing to remember, at non-dominant pole frequency, your capacitor C will act as a short circuit. If you don't do this, then the expression that you will get will be something different. Okay, so I hope that particular point is clear. Now once this thing is clear, let's look at one more sum from this assignment, that is to determine the phase margin of the loop that is given in the figure number 2. Okay, so now this is the loop. So now of course we have to break the loop first, correct, because we usually calculate the phase margin while doing the loop gain analysis. So this is the expression of the pole 2, this is the expression of the 0, this is the expression of the pole 1 that I have got, and this is the omega u that I know. So there is only 1 0 and 2 poles that are present in the circuit. So to calculate the phase margin, let me write the transfer function of the loop gain. So it will look something like this, correct. One right half plane 0 is there. Why right half plane 0 is there? Because remember the current direction. Okay, so the current from this particular branch is coming from left to right, and the current from this particular branch is coming from right to left, correct. So because of this you have a right half plane 0. If there were two parallel paths where the current would have been added in the same direction, then you would have got left half plane 0. Please remember this is really important. Okay, Now once this thing is done, so now how can you obtain the phase margin from this? So first let's calculate the phase of this transfer function. So it is nothing but minus of tan inverse of omega by z. Why minus? Because this is a right half plane 0, and then from each of these poles you will have this particular contribution. Correct? Now the important thing to note over here is, since your omega u may be much greater than P1, correct? Your omega u may be much greater than P1. So why am I saying like this? Because your omega UGB, the way we have seen, is nothing but the DC gain into P1, correct? So your omega u by P1 is nothing but the DC gain, and this DC gain can be very high, something like 60 dB or 100 dB, correct? So this particular term that you are seeing over here, this particular term will almost contribute a 90-degree phase at omega UGB, correct? So the only two terms that are left which can degrade your phase margin are nothing but this 0 and this particular P2, correct? So now once this thing is clear, the Z we have already calculated, the 0 frequency, the second pole frequency, the omega u we also know because all the values have been given to me. So from here on you can easily find the value of the phase margin, correct? This term will easily contribute almost 90-degree phase shift. So if you observe that your omega u is greater than 10 times the pole frequency P1, you can easily make this approximation that it will almost contribute a 90-degree phase shift, correct? So that is how you can easily get the phase margin. Now I would like to stop here for 1 minute and just see if you guys have any doubt in this assignment number 4. Any doubts at this particular point?
Sir, can you explain the 0 part once again? Like how opposite directions and like the same direction, that I didn't understand.
Yeah, correct. So remember this Vx that you had applied over here, you applied at the negative terminal, correct? So the output is nothing but the Gm times whatever Vx you have applied. So if I talk about the transconductor, correct, the current would have been the Gm2 times Vx, correct? The Gm2 times Vx if I had applied the Vx on the positive terminal, correct? But since I am applying a Vx over here, so it will be minus Gm2 times Vx, correct? So now this negative, if I have to remove, then the direction of the current at the output has to be changed from right to left, correct? So now what I was trying to say, just give me a second, my laptop battery is dying down. Yeah. So now what I was trying to say is basically some current, let's say some current is there like this and like this. So let's say some Gm by SC is there. So for example, some SC times Gm is here, and let's say some other quantity is there. For example, let's say Vx times some other term. So let's say this is SC Gm times Vx, and let's say this is Gm times some Gm2. Let's say this is Gm1. So now what I was saying, if I had applied this Vx at a positive terminal, the direction of the current at the output would be from left to right, correct? It would be from left to right. So now all it matters is how you are summing up the two currents. How you are summing up the two currents. So if it is like I1 plus I2 equal to 0, you know that I1 will be nothing but minus I2, correct? And now one of these two terms will be a frequency dependent quantity, correct? So if one of this term has expression which looks something like SC times Vx, correct, and other term the I2 is nothing but Gm2 times Vx, correct? So now you can see because of the negative sign, the S quantity, the S will be negative. S will be negative. Why did this happen? Because two currents were adding up in the same direction. Now instead of that, if I have something like this, let's say this is I1, and let's say the other current is actually going in this particular direction, correct? So now I can also make this diagram look something like this. This is I1, correct, and this is minus I2 that is flowing in the right direction, correct? So now since I have to sum up the current to 0, so it becomes something like I1 minus I2 equal to 0. So now this came what? I1 equal to I2. Now even if one of it has this particular term SC times Vx, there is no negative sign that you will get in this particular expression which can make the 0 to occur in the left half plane, correct? The left half plane means the S equal to negative, correct? Remember your 4 quadrants, correct? This is the S that we are talking about, correct? If your S occurs somewhere here, then you know that your S is negative, correct? This is what I was meaning when the currents are adding up in the same direction. When the currents are actually adding up in the same direction, you will get a left half plane pole, and when the currents are adding up in the same direction, correct? Sorry, when the currents are adding up in the same direction like this, you will get a left half plane pole, and when the currents are adding up in the opposite direction, you will get a right half plane pole. Correct? It is nothing but a very easy what I have shown you, the I1 equal to minus I2. So from here you can see you will get a negative sign for the S. Correct? So just imagine this, the quadrant, the when does the S becomes negative, when does the S becomes positive, and just remember that to get a left half plane 0, your S has to come out to be negative. Your S can come out to be negative only when the two currents are adding up in the same direction, because remember one of the current will have a frequency dependence, correct? So that is what I was trying to say. Is it clear, or you still have some doubt?
Yes, sir, but I'm clear, sir, but the current flowing into the transconductance is from right to left. It's going
the current
inside the
flowing
transconductance.
from the transconductor, at the output, you can see it is from right to left, yeah.
Okay, sir, but the current flowing in the capacitor is also from right to left, no, sir? Because the terminals
Oh,
are noted.
no, it is, see, where are you adding? You are adding at this particular point, right?
Yes, sir,
You are adding the where the current summing is happening, it is happening at this particular point. So the current is coming like this, correct? One current is coming like this, and other current is moving away from the node, correct? So now
Sir, but current through the capacitor is also like in the opposite direction, no, sir? Because the terminals are inverted for the first transconductor. Because
sorry,
current will be going into the first transconductor, no, sir?
sorry, can you repeat?
The terminals of the transconductor 1 are inverted. What I feel is that capacitor current will be in opposite direction.
See, that is okay. That is okay. But the zero, whatever is there in the previous stage, we are not even it will not even matter, because if you look at this particular expression, right, the Vx is ultimately gonna get cancelled. Vx is ultimately gonna get cancelled. So the polarity of Vx does not matter in this case, because Vx is gonna ultimately get cancelled. We are not trying to find out the Vx. We are trying to find out a frequency where the summation of both this term will become equal to 0. So you can also assume the Vx to be negative, but the thing that is going to happen is now this current will flow in this left direction. Correct? The current from the capacitor will now, its direction will change, it will move from right to left, but you are forgetting that if you change the polarity of Vx, the current that will come at the output of the transconductor, even that direction is gonna change. Correct? So for example, let me just see. So if you are, so what is going to happen? Let's say the two currents were something like this when the Vx was positive. Correct? Now when the Vx is negative, what is going to happen? The top current will change its direction from right to left, but the bottom current will also change its direction from left to right. So it does not matter. What is actually happening is both these currents are still remaining in the opposite direction, right? So when both these currents are remaining in the opposite, you are bound to get the right half plane 0. Correct? So that is why I was saying the polarity of Vx will not matter in this particular case.
It is clear now, sir. Thank you.
Yeah, very good. Yeah. Any other doubts, guys? Okay, great. I guess we can move with the assignment number 5 then. So again, the assignment number 5 has the same kind of circuit, but now in this particular thing, they asked you one good question, that they asked you to calculate the value of C to get a particular amount of phase margin, correct? So that particular kind of question was not there previously. So now what they are asking is the op-amp is Miller compensated for the phase margin of 45 degree in a unity gain configuration, correct? Now I will just ask you one question. This is a Miller compensated op-amp, correct? This is not a feed forward compensation. So if I, instead of doing a unity feedback over here, if I do a feedback factor, let's say something like 1/3 or 1/2, what do you think what will happen to the phase margin? It will improve or it will degrade? What do you think?
Sir, can you come again, sir?
Yeah, I was just saying is, see, this is a unity gain feedback, correct? So now I was just saying, instead of putting a unity gain feedback, so in the unity gain feedback, the beta is always equal to 1, correct? So now you compensated the system for beta equal to 1. Now I was saying that instead of connecting like this, if I had taken some resistive divider arrangement which looks something like this, correct, from the output of the op-amp, correct, from the output of the op-amp, and then from here I would have taken the output and then I would have connected in the feedback manner something like this, correct? Now I have changed,
will decrease.
the phase margin will
Decrease.
Just think again. Just think again. That means the concepts are not clear still. See, the entire reason why we do the phase margin, we do the compensation for the unity gain feedback was to make sure that we have compensated the system for the worst possible case. Correct? This is the worst possible case. Correct? Because your feedback is the strongest in this particular case. Correct? Whatever output, whatever change will be there at the output, the same change will occur at the input as well. Whereas in this particular case, what is going to happen? Whatever change is there in the output, it will get attenuated by this factor. Correct? And this particular, after attenuating by this particular factor, then this particular change is gonna apply at the input of the op-amp. Correct? So now what is the worst case? So if I'm directly connecting the output to the input, that is very dangerous. Correct? Because whatever things are happening at the output, whatever changes are happening at the output, the same are gonna appear at the input. In this particular case, at least I am attenuating it by some factor. Correct? So please do not make this mistake. The unity gain feedback is the worst possible case that you can have for a phase margin. Correct? I am talking about the Miller compensation. I am not talking about the feed forward compensation. You cannot generalize this particular concept for the case of feed forward compensation. Correct? In the feed forward compensation, if you put a feedback like this, the system may become worse. The phase margin may even degrade. Correct? So please do not make this mistake. This concept should have been clear. Correct? Because I have taken so many sums in the week 4 and week 5, and even sir has done it. So if you have solved the assignments, this doubt should not be there. So please, if still the doubt is there, please go back and please revise this concept. Okay? Now once this thing is clear, let's see what kind of questions they are asking. Determine the value of C in picofarad to achieve the desired phase margin. So we have already seen this expression of the phase margin in the last question. Correct? And what we have decided is basically this omega u by P1. So this is nothing but the ADC. So this particular quantity is going to be very huge. So the phase contribution from this particular term is going to be 90 degrees. So that is why I have written 90 degree over here. Correct? So now they are asking me to get a particular phase margin. Correct? So I have inserted a 45 degree. This is what they are telling me. Correct? Now once you do this, you will get this particular kind of expression. Correct? You will get this particular kind of expression. So now what they are asking me is to calculate the value of C. So first what I have to do, I have to represent this omega u, P2 and the 0 in terms of the expressions that I had calculated. Correct? So these are the expressions that I know. The Gm by C, the Gm2 by Cl, the Gm2 by C. This is the expression for the pole 1 and this is the expression for omega u. So now what I will do is I will substitute this omega u by P2 by putting these expressions, right? By putting these values of the expressions, and the final expression that you will get, it will look something like this. Correct? Now there are two important things that you should note in this particular case. Correct? If your CL, if your load capacitor increases by a huge factor, correct, your phase margin actually degrades. Correct? Your phase margin actually degrades. And if the ratio Gm1 by Gm2 also increases by a good factor, then your phase margin also degrades. Correct? So when you design your amplifier, you usually make sure that Gm2 will be something like 10 times of Gm1. Correct? To make sure that the phase contribution from this particular terms and also this particular quantity inside this term will be negligible. Correct? And at the same time, I also have to make sure that the CL by C ratio is also small so that my phase margin is actually high. Correct? So now once this thing is known, the Gm1 is known to you, Gm2 is known to you, the CL factor has been known to you. The only quantity that is unknown is C from here. Correct? The 45 degree is also known over here. Correct? So now you, from this particular expression, you can easily find out the value of C that is required to yield a 45 degree of phase margin. Correct? Now one more thing from this question, if you calculate the values, what you will be able to find out is your 0 will be something like lying at a 10 times of your omega UGB. Your P1 is at least smaller than 10 times. If you, what I was saying is basically if you multiply, this is not correct. Yeah. So what I was saying is your omega U is actually greater than the 10 times of P1. Correct? So now what I was saying is, let's say your system, the magnitude plot, it looks something like this. Correct? And here you have a P2. Correct? So around the omega UGB, your system is acting like a first order system. Correct? Now in this particular case, you will get a sufficient phase margin. Okay. Now the quantity that they have mentioned is you are getting a phase margin of 45 degree. Correct. Now remember this, whatever phase degradation this pole had to cause, it has already caused, correct, by contributing a 90-degree phase at omega UGB, because it cannot contribute more phase than this particular quantity. This is the maximum that a pole can contribute. The other term that can degrade the phase margin is basically nothing but these two, correct? Correct, the pole and the zero that you have, correct? But if I ensure that but if you calculate the values, what you can also find out is, once you get the C, correct, once you get the C from here, what you can easily also see is that your Z will be greater than 10 times of omega U. So once this is clear, you know that the zero will not do any phase degradation at omega UGB. Correct. Now the only quantity that is left is a P2. So how can you make sure that the contribution of this particular pole at omega UGB is just 45 degree? Correct. So now I will just ask you one question. If I try to make a phase plot, of this, correct? So I have to start from the zero, correct? Now what will be this contribution? So if I try to track the phase at P1, correct, if I want to get the value of the phase, correct, at P1, what is this phase going to be? What is this phase going to be? What is this value?
45.
Yeah, minus 45, correct? So this is minus 45. So this is what I was trying to say, is at pole frequency, you are basically getting a 45 degree of degradation, correct? Now already a 90 degree of degradation has happened because of the pole, correct? Now if I put this particular pole P2 exactly on top of my omega UGB, correct, then what is going to happen? This pole P2 will contribute a 45 degree of phase degradation. So 90 degree came from pole 1, 45 degree came from pole 2. The net phase became minus 135 degree. So if I add 180 degree over here, my phase margin is equal to 45 degree. And this is what the question is also mentioning. Correct? This is what the question is also mentioning. So what the entire point of doing this analysis was to tell you that in this particular case, the omega UGB, this particular omega UGB will be exactly equal to P2, because if you don't do that, correct, if you move the pole away from the omega UGB, your phase margin will be greater than 45 degree. And the question has asked you to design exactly for 45 degree phase margin. So if you equate these two, correct, if you equate these two, this is a shortcut method that you can use to find out the value of C from here. Correct? But remember, that can only happen when the zero does not contribute anything over here. Correct? So your zero has to be at least 10 times greater than omega U. And only when you know this, then you can apply. Otherwise, you have to go with this particular method only. Correct? So I hope that particular point is clear, how to approach the question and how to find the value of C. Now once this thing is clear, again we will do the same thing. After solving the assignment 5, we will take 1 minute break and see if anybody has any doubt. Now they are asking us determine the value of the unity gain basically they are asking us to calculate omega UGB. Correct? We know how to calculate the omega UGB. The DC gain we already know, GM1 by GO1. Correct? What about this particular quantity, the value of the pole, the omega P1? The omega P1 is not at all affected. Remember what has happened to the P1 over here. Correct? So this particular P1, now what I was saying is, once you know the value of C, let's say you got the value of P1 from here. Now what you decided to calculate the loop gain. Correct? Now I just wanted to check if this particular expression of omega P1, correct, if this particular expression of omega P1, it will get affected by the loading, if I make any changes in the loading or not. Correct? So now why I was saying like this, because remember, compared to the week 4 assignment, the value of the CL is changed over here. Correct? Previously this was 1 picofarad. Now this time it has become around 10 picofarad. Correct? Now how to find out the value of the unity gain loop frequency? The DC gain you can easily find out from this particular quantity, and the value of the omega P1. Correct? The value of the omega P1 you can easily find out from here. So again the unity gain loop frequency is nothing but your GM1 by C. Correct? C you have already calculated from the previous question, right? From the phase margin. So the moment you put that value of C over here, you can easily find out the value of unity gain loop frequency. Correct? If you don't want to remember this particular expression, then you have to find out the DC gain multiplied by the omega P1, and the reason for this I have already explained, why this particular quantity gives you the omega UGB factor. Correct. Now the next thing is they are asking us to determine the position of the dominant pole of the loop gain. Correct. So the dominant pole of the loop gain will also occur at this particular node over here. Correct. Because this particular stage has a lot of gain. Correct. This particular stage has a lot of gain. So the amount of effective capacitance that I will see over here is going to be huge. Correct. This is going to be huge. So that is why the dominant pole will be represented by this particular expression. So remember how this expression has occurred. So this expression was nothing but 1 by Rho1 times C into 1 plus whatever gain is there at the stage 2. And remember this gain of the second stage, this gain changes with the loading, correct? Changes with loading. So what do I mean? If you unload your amplifier, if you remove the load, then this gain will be higher. If you put some RL, correct? If you put some RL in parallel with the Rho2, then this gain is gonna reduce a little bit depending on this value of the RL. Correct. So that's how once you know everything, you have calculated the value of C, you know the gain of the second stage, correct? Because you know this value, each and everything has been given in the question, correct? GM2, GO2 as well as the GL. So you know the value of AV2, you know the value of C. What about the Rho1? The value of GO1 has been given in the question, correct? So that is how you can easily find out the value of P1. One more thing, you can do one more shortcut. How can you do the shortcut? You know ADC times the value of P1 is nothing but omega UGB. If you know the omega UGB that you have calculated in this particular question, you also know the DC gain, correct? So from here on, you can also find out the value of P1 without having to do all these calculations, correct? This will give you the answer in one step only, correct? This is just a one step answer. But do not apply this, do not only and only apply this if you know that the Bode plot of your system is gonna look something like this. Okay, around the omega UGB, the system should behave as a first order system. If you have two poles before the omega UGB, then this expression will give you incorrect answer. Please remember this. Okay, do not apply this expression blindly. You have to check the Bode plot of the system first. Okay, once this thing is clear, now the next question they are asking is, the CL is now increased to 20 picofarad. Initial value was 10 picofarad. Now they are making it to 20 picofarad. Correct? So now they are asking us to determine the new position of the non-dominant pole of the loop gain. So first we have to first write the expression for the non-dominant pole, which is nothing but the GM2 by CL. Correct? And now we have to see whether this expression depends on CL or not. So now if the CL has been increased by the factor 2, if I make this increase by the factor 2x, my pole, the non-dominant pole will decrease by the factor 2x. Correct? So if you know the non-dominant pole from the previous calculation, you just have to divide your answer by the 2 to get the final answer. And remember, they are asking us to calculate the values in megahertz, not radians per second. So final answer, whatever you get, correct, the P2 has to be divided by 2 pi to get the answer in megahertz. Okay, now one more thing is, after that they are asking me to calculate the new position of the non-dominant 0. There is only one 0 in the system, and that 0 is nothing but GM2 by C. Even if I increase the CL by the factor 2x, which the question has asked us to do, correct, this expression does not depend on the CL, correct? So the 0 is not affected by whatever I do on the loading side. It is only affected by GM2 and this compensation capacitor C, correct? So, and the reason for this is basically the I1 and the I2, correct? The two currents, wherever they are summing, correct? The thing is, your CL is appearing somewhere over here. These two currents, they are independent of what you do at the CL, correct? This is dependent on what is your compensation capacitor C. This is nothing but the output of transconductor GM2. Just a minute, yeah, output of transconductor GM2, correct? So none of them is dependent on CL over here. So that is why you can see the 0. It also intuitively makes sense that why it should not depend on the CL. Now the next thing is, determine the value to which the compensation capacitor should be increased so that the phase margin is restored to 45 degree. First of all, we have to ask ourselves, why do I need to increase the compensation capacitor? Correct. So for that I have written this expression of the phase margin. This should be very familiar to you now. The phase contributed by this particular term, correct? This particular term, it is nothing but going to be 90 degree. Correct. Now I have two other terms over here. From the expressions of omega u, p1, p2 and 0, I have inserted all this in this particular case, and this is the expression that I got over here. Correct. This is the expression now that I have got in this particular case. Guys, are you still able to see my screen, or it is not visible to you? Guys, is my screen visible? Guys, is my screen visible to everyone? Guys, am I audible? Is my screen visible to everyone?
Yeah, sir.
Okay, good. So I guess we are good to go. Yeah. So So what I was saying was, if you look at the expression for the phase margin, right? What I have done is I have inserted all these equations, the P1, P2, and omega u, and this is the expression that I got for the phase margin. So what you can see, if my CL starts increasing, right, then the contribution of this term is gonna increase. This term has a negative sign, so the phase margin decreases if my load capacitor increases. Correct. So now I don't want to change my GM1, I don't want to change my GM2. The smart thing that I can do is, whatever factor by which I have increased the CL, with the same factor I can increase my C as well. Correct. So the net contribution, the net increase from this particular term will become 0, and my phase margin will be restored to its original value. Correct. So what we can see now is determine the value to which the compensation capacitor C should be increased. So what we can find out, since CL has been increased by the factor 2x, we also have to increase the C by the factor 2x. Only then we won't have any significant effect on our phase margin. Correct. So whatever C that you got from the previous question, so just multiplied by the factor 2, you will get the answer for this particular question. Correct. Now the next thing they are asking is to determine the new unity gain loop frequency. Now remember, our unity gain loop frequency is dependent on C, and how it is nothing but GM1 upon C. Correct. It is nothing but GM1 by C. If you want to get an intuitive understanding, remember, even if you increase the CL or factor C, correct, your DC gain ADC, it remains constant. It remains constant. But if you increase the C, correct, if you increase the C affects the dominant pole of the circuit. Correct. So if the C affects the dominant pole of the circuit, then my pole P1 will start approaching towards the lower frequency. What is your omega UGB? It is nothing but ADC times P1. Correct. So if ADC remains constant and my P starts to reduce, even my omega UGB will start to reduce. Correct. So that is why this equation is also making the sense. If you increase the C, the dominant pole of the circuit reduces, the 3 dB bandwidth of the circuit reduces, and because the 3 dB bandwidth of the circuit reduces and the DC gain remains constant, even your omega UGB is gonna reduce in this particular case. Correct. So if your C is increased by the factor 2, then your omega UGB will also reduce by the factor 2. Correct? I hope this point is making sense to everyone. I would like to stop here for 1 minute just to see if anyone has any doubt in this, whatever question we have solved for assignment 5. It was just an extension of what we have seen for the case of the assignment 4. The only thing is we had to calculate the value of the C. The question was inverted. We had to design the amplifier, that is to find the value of the compensation capacitor to get a particular value of the phase margin. Then they increase the load capacitor, and when they increase the load capacitor, again they asked us to find out the positions of the dominant pole, the non-dominant pole, the zero, and what should we do to restore the phase margin. Then we found out that the compensation capacitor also needs to be increased by the factor 2, but doing so also reduces your omega UGB and the 3 dB bandwidth of the circuit. Correct? Any doubts at this particular point, guys? This is a good time to ask the questions. Everything is clear? Everything is clear, or everything is going above your head? I just need some feedback. Sorry, I'm not able to hear you. Shall I move ahead? Everything is clear?
Sir, can you just like describe the phase margin part again?
Okay, sure, yeah. So, if you, is this expression clear to you, this particular phase margin expression?
Yes, sir. It
Yeah.
comes
So
from
now-
the transfer function only.
Yes, it comes from the transfer function. Very good. So now what I have done, these expressions we have already calculated from the assignment 4, right? The question that we had saw. The expression for the P2, the 0, the P1 and the omega U. Remember why am I doing that? Because question has mentioned something. They are asking me to find out the new value of the compensation capacitor so that the phase margin is restored. So if you just apply a little bit of logic, so if I don't increase the value of C, the question, what this question is asking me, the question is mentioning that your phase margin is gonna degrade. Correct? Now I have to check why is it happening so. Correct? To check why increasing the value of the load capacitor is decreasing the phase margin, I have to represent this equation in terms of CL. Correct? So to represent this equation in terms of CL, what I have to do, this omega U, P2, P1 and 0, I have to substitute their equations. These equations I am talking about. The moment you substitute these equations, now you have brought your phase margin as a function of CL, C, GM1 and GM2. Correct? Now what you can see, this is the part where this particular part contains the CL as well as the C. So now if you increase your CL, correct? If you increase your CL, correct? So basically how does the tan inverse of x behaves? If x increases, even your tan inverse of x is gonna increase. Correct? You agree with this, right? So once this particular quantity increases, remember this quantity is in a bracket. Correct? This bracket contains 3 terms and outside the bracket there is a negative sign. So if this particular term increases, then the phase margin is gonna reduce. Correct? So first, whatever the question was mentioning, that if you increase the CL, then your phase margin is gonna degrade. That is true, because this is the same thing that I am seeing from this particular equation. Now what this question is asking me to do is to calculate the new value of the compensation capacitor, so that your phase margin, whatever it has degraded to, it is now restored back to 45 degree. So now what did I do? If I increase the factor CL by 2x, correct? So how can I make sure that this term, the degradation due to this term is 0? I just have to make sure that the ratio of CL upon C is constant. Correct? If I make sure that the CL upon C is constant, then the net degradation from this particular term to the phase margin will be 0. Correct? Now if I increase the CL by the factor 2, correct, what should happen to the C for this particular ratio to remain constant?
2 times.
2 times, right? So that is the same thing that I have done over here. So that's why I have written that if your CL increases by the factor 2, then you have to also increase the compensation capacitor by the factor 2 to make sure that the phase margin is restored. Is it clear now?
Yes, sir. Yes, sir. It's been.
Yeah, excellent. Very good. Any more doubts, guys, in this till this particular point? Okay, good. I guess we will go to the next assignment. Please feel free to poke if you guys think that some part is still not clear to you. Correct? So now what I will do from this particular assignment, this input offset, the input bias current, the offset voltage and all, you will find tons of literature on the YouTube and all. You can also find a lot of questions available on the YouTube where people solve gate questions and all. Correct? So I won't be solving this because it will take a good amount of time. I will do the tough part for you. So this is the question that I will be solving. Correct? So now what this question is asking you to do, it's some smart student, just because he had learned a CMOS inverter, correct, he used 3 CMOS inverters cascaded and he thought that he can use this circuit as a op-amp. Correct, he can use this circuit as a high gain amplifier, then he can use this amplifier and construct a feedback network around it so that it behaves as a some kind of non-inverting amplifier, non-inverting or inverting amplifier. Okay, so now what this question is asking you to do is, so basically this is the description that I had given. So what they are mentioning is, for each and every stage the GM and the R0 has been given to you, correct, and along with this each and every stage represents an output capacitance of 10 picofarad, correct. So everywhere over here, correct, if you look at one particular stage, this is the GM of the circuit, this is the R0 of the particular stage, and this is the load capacitance, correct. So this is just a one stage. Now there are 3 stages in cascade, correct. Now what it is asking us is to what is the magnitude of the DC gain of the op-amp. Remember, they are not asking us to calculate the DC gain of this circuit. They are asking us to calculate the DC gain of the op-amp. Op-amp is nothing but only this particular part of the circuit, correct. Op-amp is nothing but only this particular part of the circuit. So now I have just simplified it over here in this particular case. So since I am talking about the DC gain, I can open circuit all the capacitors that are present in the circuit. The gain of each stage will be nothing but GM by G0. Since there are 3 stages in cascade, the gain of each and every stage will be multiplied. So this will become nothing but GM by G0 whole cube, correct. GM is 10 millisiemens, the G0 is 0.5 millisiemens, correct. So this ratio will be nothing but 100 upon 5, which will come out to be 20. So the cube of it will become nothing but 20 into 20 into 20. So this became equal to 8000. So this is the DC gain of my circuit in volts per volt, correct. Always remember the units. If it has been asked in the terms of dB, it would have been 20 log of 8000, correct. Remember, this is a voltage gain, this is not a power gain, okay. If you are calculating the power gain, it is something like 10 log of Gp. Since this is a voltage gain, this is a 20 log of something, okay. Now once this thing is clear, now it is asking me to calculate what is the phase margin of the closed loop amplifier in the degrees, correct. So what I have done, I have just taken these amplifiers, I have just represented the load resistance and the capacitance that is present at the output of each and every stage. And now what I have done, since first I have to calculate the transfer function, only then I can get the phase, correct. So this is the DC gain, correct, that I can write without even worrying about the frequency. Now if I want to include the frequency term, remember each and every stage is contributing this particular pole over here, correct. So the poles of each and every stage are identical, so it will become 1 plus S by P the whole cube. Now if I try to write the phase of this particular quantity, it will become what? Minus 3 times tan inverse of omega by P. Why? Because 3 poles are there at a same location, correct. So now if I add 180 degrees on it, then I will get a phase margin of this particular circuit. Now I will say this is a phase margin that I have derived, but I am telling you that this is wrong. What question has asked and what I have done, it is wrong, completely wrong. Can anyone tell me what is the wrong in this particular thing? What wrong thing I have done over here?
They asked for the closed loop, I guess.
Excellent, excellent, very good. So now they are asking for the closed loop, and remember, we calculate the phase margin. This is seeming like a closed loop amplifier, but remember, you calculate the phase margin by doing the loop gain analysis. That particular phase margin, you ensure that you have some finite phase margin left with you, so that when you close the loop, correct, when you close the loop, your system will not oscillate. Correct. So the phase margin analysis is always done on the loop gain, not on the, what you can say, not on the just the naked amplifier, or not on the complete closed loop system. Okay, this phase margin we do it for the loop gain analysis, just to make sure that we don't have to calculate the complicated expressions for the closed loop poles. Without doing those complicated calculations, can I devise a method in the loop gain analysis itself, so that just by doing the loop gain analysis I can find out whether my system is stable or not. Correct. We have to do it for the loop gain. I have not included any loading effect on this particular diagram. Correct. So this guy caught me red-handedly, and he caught me within 5 seconds itself. Correct. So he did a very good job. So now what we have to do is we have to load the amplifier. Now first we have to calculate the loop gain of the circuit. Correct. So what I have done over here, this is my amplifier that you can able to see over here. To do the loop gain, what I have to do, I have to break the loop. Where should I break the loop? You should break the loop at a point where you will see a high impedance. At the input of the amplifier, I will see a very high impedance, correct? So I decided to break the loop over here. I am applying a V-test voltage over here. I just have to see what voltage comes back, correct? So now what you can see over here is this is the amplifier that I have. So this is nothing but my op amp, correct? So in this particular figure now I will be replacing this A with the 3 stages that I know, correct? So this is how it will look. Now at the output I also have R2 and R1, and the output is taken at the R1 node, correct? At the R1 node. So this is where I am taking the output. So the loop gain is nothing but Vx upon Vtest, correct? Vx is coming at the output of the R1 and Vtest is coming at the input. Correct. What you can see over here, the loading for the third stage has changed now. Correct. It is not only R0, it is R0 in parallel with R2 plus R1. Correct. So if I write the DC gain now, correct, if I write the DC gain, it will look something like this. GM of the first stage into R0. This is coming from the first stage. Then in the second stage I have GM into R0. This is for the second stage. And for the third stage I have GM into R0 in parallel with R1 plus R2. Correct. This will be coming for the third stage. I hope it is making sense to everyone. Okay. Any doubts? Please feel free to poke me at any point. So this is what I have written. The GM times R0 square for first and second stages. Correct. This is for the first and this is for the second stage. And this expression that you are seeing, it is for the third stage. This is what I have written over here. Remember the poles for the first at the output of the first stage and at the output of the second stage, they look exactly identical. Correct. That is why I have square over here. That is why I have square over here. But if you look for the third case, right, then the expression for the pole over here is nothing but 1 upon R0 in parallel with R1 plus R2, correct, multiplied by the C. This is the expression for this pole. I am denoting it as pole number 2, correct. So this is what you can see over here, and all the quantities have been written in this particular case over here. So now apart from this, there is one more thing that we are forgetting. So what will be the DC gain of this circuit? See, what I have written over here, it is the V0 by Vtest. But where am I taking the output? Am I taking the output at V0 or am I taking the output at Vx for doing the loop gain calculation? Where am I taking the output? Vx, right? So I don't have to find V0 by Vtest, but I have to find Vx by Vtest. So how V0 and Vx are related to each other? Just look over here. This is V0, this is Vx. It is a simple resistive divider, correct? So that is why you can see I have, when I write from V0 to Vtest, whenever I am moving to Vx by Vtest, I have a factor of R1 divided by R1 plus R2, correct? And this is the reason for it. So now you got a loop gain expression. And from here you can find out everything. The DC gain, you can find out the location of the pole P1, P2. You can also find out the expression for phase margin over here. Correct? So now let's find out the DC loop gain first. So if I put S equal to 0 in this particular case, you can see I will be just left with this particular term. Correct? I will be just left with this particular term. And this is what I am writing over here in this particular page. Correct? Correct. So now this is the DC loop gain of my circuit. What about the phase of the circuit? The phase of this loop gain, the phase will be nothing but the minus 2 times tan inverse of, let's say, omega u by P1. This will come from this particular term, and this term will contribute what? Minus of tan inverse of omega u by P2. Correct? It will contribute omega u by P2. Now one more thing. Now just tell me, since I am doing the loop gain analysis over here, correct? Will there be any zero in the circuit? Are you able to see any two parallel paths?
No, sir.
No, right? So that's why there is no zero that is present in the circuit actually. Correct? So I hope that particular point is clear. Now once this thing is clear, this is how I will be able to get the phase margin equation. Now, I already told you how these two terms came up over here. Now once I add 180 degree in it, then I will get the phase margin equation. Now before calculating the phase margin, remember the P1, the pole P1 I know, the pole P2 also I know, because I know the value of RL, I also know the value of R0, I also know the value of C, correct? And I also know the value of the CL if some loading is there at the output. So from there I know the value of the P1 and P2, they will come in radians per second. But what about omega u? I don't know the value of omega u yet, correct? I don't have any means to calculate the omega u. So first I have to do something to calculate omega u. I will tell you two methods, okay? You decide whatever you want to apply. So this is the loop gain that I have. Let's go with the very accurate method. So what is the definition of the loop, the unity loop gain frequency? So the frequency at which the magnitude of the loop gain becomes 1. So at that particular frequency, I call it as a unity gain loop frequency, correct? So what I'm gonna do over here, I'm gonna take the mod of this particular term, this entire big expression that you are seeing. So the entire DC, whatever DC terms are present in this equation, I have just replaced it by a loop gain DC. This is the expression that you are seeing over here, correct? And then I have three poles, two poles at the same location and one pole at a different location. So if I take a magnitude of this, correct, then what you will be able to see is there will be a square root for this particular term, and since this particular term has a square, this square root will be gone for this particular term over here, correct? So now at this particular frequency, I know that the loop gain will be equal to 1, correct? So now this I can take this denominator on the right hand side over here, correct? And I can square on both the sides, correct? I can do squaring on both the sides, correct? Now what I have is I want to find out the omega u over here, correct? But if you try to multiply these two terms, correct, what you will get is a 6th order polynomial. You will get a 6th order polynomial. In the exam there will be a no way for you to solve this particular expression, correct? Now what I can do is I can replace omega u square by some particular quantity x. I can replace it with some particular quantity x, and then I can put a separate expression. But still you have a cubic expression. Unless until you solve this cubic expression, you will not be able to get the value of x. And if you don't get the value of x, then you will not be able to get the value of omega u, correct? So if you have a calculator, or if you want to apply a Newton-Raphson method, some numerical methods, you can definitely do this method. But in the exam, it is gonna consume a hell lot of time, correct? So you can also do a separate and easy and approximation, apply some approximation, correct? Now what you can do is, if you have two poles, correct? If you have two poles that are occurring before omega u, correct? Then how can I write the expression? How can I write the expression over here? Remember, after I hit the pole P1, what expression I will get? If I ignore other poles, so it will be a0 upon 1 plus omega by P1 the whole square, correct? Now if my omega is much higher than P1, I can simply write this expression as omega a0 into P1 by omega. Now if there are two poles occurring at the same location P1, now this will be changed to a0 into P1 by omega the whole square, correct? Now this is only valid between P1 and P2, correct? When omega is lying between P2 and it is much greater than P1, correct? This is the case when this expression is holding true. After P2, now how can I write the expression? Now at P2, correct? Now I know the gain at this particular point, correct? What is the gain? A0 into P1 by omega the whole square. Now from this particular point, now the gain will again start to roll off because P2 will add its own roll off. Correct? So that roll off, similarly, just like I have written a expression like this, similarly you can write like P2 by omega, right? Now, and remember the A naught in this expression was the gain at which the pole had actually occurred. Now the gain at which the pole P2 is occurring is actually nothing but A naught into P1 by omega the whole square. Correct? Now when I multiply P2 by omega with this particular quantity, this is how my gain will be approximately rolling off for the frequency which is you can say much greater than P2, and of course it is much greater than P1 as well. Correct? And this is somewhere here your omega UGB will occur. Correct? So this expression will hold approximately true given my omega is much greater than P2 and much greater than P1. Now if I substitute omega equal to omega u, correct? By the way, what is this expression? This is the expression for your loop gain. Okay, loop gain of j omega. So now if I substitute omega equal to omega u, my loop gain becomes equal to 1 at that particular frequency. Correct? So that is why I have represented 1 over here, and omega I will be substituting with omega u. Correct? So now from here on you got a very simple expression for omega u, where you can easily calculate the value of omega u just by solving this particular expression. Correct? You know the value of A0, you know where the poles are occurring, correct? And from here you can calculate the value of omega u directly. Correct? So that value will come out to be something like 48 into 10 to the power 7 radians per second. This value will differ from what value you will get from this exact method. Correct? But remember that variation will be somewhat small, maybe 10% or maybe 15% of error will be there, not more than that. Correct? So this is a very simple method using which you can actually approximate the value of the unity gain loop frequency. Correct? Now once this is done, once you know the value of omega u, you know the P1, you know
Sorry to
the
interrupt you.
sorry, yeah.
Yeah, sorry to interrupt you, sir. Sir, can you just like briefly tell this method again? I'm like, it's like too much things in my mind. I can't understand.
Oh, okay, no problem. So shall I go from the start over here?
Yes, sir. Yes, sir.
Okay, so remember you just unmute your mic. I will just ask you a series of questions in steps. So you remember this equation, right, that I had discussed in while solving the assignment 4?
Yes, sir. Yes, sir.
Yeah, you remember this. Now if my omega is greater than P1, I can ignore this one factor.
Yes, sir. Yes, sir.
Correct? Now if I ignore this one factor, this square and this square root will be gone. The P1 will come in the numerator.
Yes, sir.
Correct? That is why this you got A0 into P1 by omega.
Yes,
Correct?
sir.
Now when does this equation holds true? This holds true only when your omega is much greater than P1 and lesser than P2, because remember we have not taken any effect of P2. So what this equation represents is loop
Only
gain
one
of
pole.
yeah, only one pole, and this loop gain equation is only valid only in this particular region. Only in this particular region. Okay.
Okay, sir.
Yeah. Now what I am trying to do now, okay, I know how my loop gain is rolling off. So I know that P2 will be somewhat greater than P1. Correct? So what I am trying to say over here is now I have reached this particular point over here, and still this equation is holding true. Correct? So at that particular point, my gain is A0 times P1 by omega. But remember, at that particular omega, my omega is nothing but P2. Correct? So this is the gain that you have now at this particular point.
Okay, sir.
Correct? Now at this particular point, now P2 will do its own stuff, just like the pole P1 contributed A0 into P1 by omega. Correct? The pole P2 will also contribute the same thing. So now whatever gain, so I will just write whatever gain is available at omega is equal to P2. So when I multiply this by the factor P2 by omega, correct? Now this equation will be now valid for omega greater than P2, much greater than P2. Do you agree with this? If I just tell you that some gain is available at the frequency P2, correct? Some gain is available at frequency P2. Now that gain multiplied by the P2 by omega will be nothing but the loop gain expression for frequency ranges greater, where omega is much greater than P2. Are you able to digest this, or some doubt is there in this?
I'm still not able to get it.
Okay, no problem. So, did you get this expression? A naught into P1 by omega?
Yes, sir. Yes, sir.
Yeah. So from where did this came? You can easily write this without doing all this analysis, without doing this square root and all. You can easily write this by looking at only A naught and P1. Correct? So A naught is nothing but whatever gain I have at pole frequency P1. Correct? Are you
Yes, sir.
getting this?
Yes, sir.
Now, when I multiply this by P1 by omega, why P1 by omega? Remember, my gain has to roll off. As I increase in frequency, my gain has to roll off. That's why the omega is there in the denominator and not in the numerator. Is it making
Okay.
sense?
Yes, sir. Yes, sir.
Yeah. So similarly, if I look at the pole P2, just like A naught gain was available at omega equal to P1, let's say some gain is available, and what is this gain? I am denoting it as A at omega equal to P2. I don't know this right now. Okay.
Okay,
So
sir.
what I am denoting this is some quantity, the gain that is available, loop gain that is available at omega equal to P2. Correct. So this quantity I have written like over here. Just like you had P1 by omega, correct, I will have P2 by omega over here.
Yes, sir.
Correct. So now till this point it is very much clear to you, right? How did I get this expression?
Okay, sir. Yes, sir.
Yeah. So omega is much greater than P2. Only in that particular case this expression holds true. Now my only job is to find out this particular quantity. Correct. What is the gain available at P2?
Okay, so that will
So
be A into P1 by P2.
Exactly. Very good. Now you got it. Yeah.
The same thing which we like did for the first pole, we are doing it for the second pole also.
Yes. Exactly. You got it now.
Okay, sir. Thank you, sir.
Yeah, very good. So, so now I hope that particular point is clear. Now, once you do this, now you will be easily able to find out the value of omega u. And once you got the omega u, correct? Once you got the omega u, then you can easily able to find out the phase margin. But I guess hey, this will not be A1. This will not be A naught into P1 by P2. Remember, there are two poles occurring at this particular point. The guy who just said this particular value of A will be nothing but A naught into P1 by P2. Please note that there are two poles that are occurring. So you don't have to use this expression. You have to use this expression actually. Remember, this is at P1 there are two
omega
poles.
square.
There are two poles. Yeah. So you have to use this expression, not this expression. Okay.
Okay, sir.
Yeah, at P2 it is only a single pole, that is why this expression will look something like this. Okay, so please just remember this. Yeah. Now from here you got a phase margin and you got that the phase margin is actually negative. The negative phase margin is very bad. Correct. So now we have to do something. So again they pose the next question. The next question was determine the value of C that I can put at the output of the amplifier 1. This is the C external that I want to add to stabilize the system. How will I stabilize the system? So the way, this is nothing but the dominant pole compensation. Okay. So initially it looked something like this, correct? Now what I will do, I will pull this pole. Towards the left hand side. Correct?
Move
Now
the
it
poles
will look
apart.
something- Yes, exactly. Yeah. So it looks something like this, correct? That this pole location will not change. But at least you can see my system is becoming stable now. Correct? Because at omega UG, at omega UGB, I used to check the phase. Correct? Over here, you can see that these poles, there are 3 poles before over here. But in this particular case, at least I have removed 1 pole outside omega UGB. Correct? So that's how this dominant pole compensation will work. So remember, now this is the pole that I have from the second stage. So this pole is unchanged. What about this pole? Even the pole P2 is unchanged over here. But only thing that has changed is the location of the pole P1, and that I have denoted as P1 dash. Correct? So if I write the phase margin expression, it will look something like this. Correct? Now omega u by P1, correct? Remember, if you look at the Bode plot diagram, when you hit omega UGB, correct, your P1 dash is far apart from your omega UGB. If your system behaves as a first order system around omega UGB, then you can easily say that omega UGB, correct, is nothing but your P1 dash into a loop gain of DC. Correct. So now this particular term, while getting the phase margin, this will contribute a 90-degree phase margin. Correct. So you have this particular expression left. Now remember, they have given you that you want a phase margin of 70 degree. Correct. So now from this expression, I got this expression tan inverse of omega u by P1 plus tan inverse of omega u by P2 equal to 20 degree. I know the value of P1. I know the value of P2. Remember, this P1 is the pole that I am talking at the output of the second stage. Correct. Why I have taken it as a P1? Because this is the same expression that I have taken in the previous case as well. I don't want to confuse with respect to previous case. That's why I did not change the notation of the poles. This pole P2 is nothing but this output pole. Correct. It is this output pole. The P1 dash pole is nothing but this particular pole caused by this particular RC constants. Okay, so from here we can easily find out the value of omega u. In the exam, how will you find out the value? So basically you have to take the tan of both the terms. Tan of, basically it is like tan of a plus b is equal to tan of 20 degree. What is the formula for tan of a plus b? It is nothing but tan a plus tan b upon 1 minus tan a tan b. So you have to use this expression, okay? Or else you won't be able to reach towards the final answer. So unless until you use this trigonometric identity, you will not be able to solve the questions in the exam. Okay, so from here you can easily find out get the expression for omega u and get that expression for omega u first. Now our next job is to find out the modified location of the pole. Remember, this is the expression that I had, correct? So this omega u GB, you got this from the phase margin equation that I had represented over here. Correct? You got this from this particular term. Now once you know omega UGB, you also know the DC gain. Remember, inserting the external capacitor will not change this gain, correct? It will not change the DC gain. So from here you can easily find out the location of the modified first pole that will come from the first stage, and this will be the dominant pole of the system. And now once you know the location of the dominant pole of the system, that is the P1 dash, let's write the expression for P1 dash. It was nothing but 1 by R naught into the net capacitance. The net capacitance is nothing but the external cap that I had added and the some cap that is present at the output of the stage. If I know this, from where did I get it? From this particular expression I got that, correct? So if I know P1 dash, if I know R naught, if I know the value of the C, maybe 10 picofarad that was given in the previous question, I can easily find out the external capacitance that I need to add so that my pole location shifts down, and if my pole location shifts down, my phase margin will improve, and I will keep on doing it unless and until I hit a phase margin number of 70 degree. Correct? Remember, the phase margin without doing dominant pole compensation was minus 71 degree. So I have to keep on increasing the value of the capacitor that I am adding till I reach from minus 71 to 70 degree. Correct? That is how you are going to solve the question for the omega UGB, the dominant pole, as well as the value of the capacitor that you actually require. Now the next question that they are asking is interesting one. Determine the closed loop bandwidth of the system. Correct? Remember what happens if this is my open loop system. This is acting like a first order system now. Correct? After compensation. Now if I put it in the closed loop feedback, correct, it will look something like this. Correct? It will look something like this. So what you can see over here, the 3 dB bandwidth of the open loop system and the 3 dB bandwidth of the closed loop system. So the closed loop system bandwidth is increased compared to the open loop bandwidth system. And we have already seen this expression, correct? We have already seen this expression in the first 3 weeks of the course, correct? That the omega of the 3 dB of the closed loop system is nothing but 1 plus A beta. Beta is the feedback factor. A is the gain of the open loop system, correct? If I multiply 1 plus A beta with the 3 dB of the open loop system, then I will get the expression for the 3 dB of the closed loop system. Remember, this is nothing but the DC loop gain. DC loop gain of my system, correct? So I can represent A into beta by A of loop gain DC, correct? This is a loop gain, DC loop gain of the system. And remember, your A loop gain DC multiplied by the P1, this is nothing but the DC gain into the pole of the system. This is nothing but omega UGB, correct? So what you will be able to find out is that your omega UGB will be approximately equal to the 3 dB bandwidth of the closed loop system. Omega UGB for closed loop and open loop system remains same. It does not change. The only thing that changes is the DC gain. Correct? It is DC gain. This is a loop gain. Let's say this is ADC closed loop. Correct? And other thing that changes is the 3 dB bandwidth of your system. That is the loop gain. That is the open loop as well as the closed loop system. So now I would like to stop here for 1 minute just to check if you guys have any questions.
Sir, I have a question.
Ha?
Sir, like why can't even the mistake I did in the same in assignment? Why not we calculate the loop gain through like multiplying A and beta? A is the DC gain which we got like 8,000 for the before question. 8,000 into beta is R2 by R1, right? Like if you multiply
R2
that,
by,
we can get,
beta is R2 by R1 plus R2, right?
yeah, R2 by the feedback factor.
Correct.
If you multiply that, we'll get the DC loop gain, no sir. But why
Yeah,
can't
you
we
will
do-
get, you will get, you will definitely get, you will definitely get. You can easily do that. The only thing is, since we usually do it by breaking the loop, right? Usually you can do it with the two methods. The only thing why I don't prefer that method is, let me just tell you. Let me go back. Yeah. So the only thing is, see, in this particular case, identifying the beta is very easy. Correct. So when you want to do A into beta, you have to identify the feedback network first. Correct. And then you have to remove that feedback network, then calculate the gain of the open loop system, then calculate the beta, then multiply the two. Correct. Now in some cases, if you apply the feedback, since see we have not covered the feedback in this particular course, right? There is a complete chapter on feedback in the Razavi. So if you look over there, there will be some complicated topologies where identifying beta itself will become little bit tricky in those particular cases. So that is why we usually do what? We usually break the loop and we directly calculate the loop gain. So that will be nothing but your A into beta only. That's how we usually proceed, because in that particular case you don't have to have a headache of separating out the feedback network from your open loop network and then do the calculations. So that's why it becomes actually easier.
Okay, sir. But we since have the third pole different, like we can't do that here, I guess.
Sorry?
Since we have the third pole including R1 and R2, like we can't do the A-beta analysis here, I guess, for the loop gain expression.
Just give me a second. Can you repeat? I didn't get your question.
No, sir. Like just I'm saying that since we have third pole different here, like with R2 and R1 including, we can't
correct.
multiply A and beta here.
Yeah, correct. So if you just think like if you include the A separately, if you include the B separately, so then R2 and R1 would not have come into the picture. So the pole location that you would have got, it would have also been wrong. This is what you are saying, right?
Yes, sir. That's what.
Yeah. So that why did that happen? Because this feedback R2 by R1, so it is connected across a point which is seeing a finite output impedance. So you have to take that loading factor into the account, and to take that loading factor into the account, you have to go back to that feedback theory, and in that way you can actually separate out these two, because whenever you separate out the two, the feedback factor, the feedback network and this, correct? Remember, this is not a infinite output impedance now, this is a finite one. So while you are separating these two out, while you are removing R2 by R1 from here, this is, let's say, your open loop network now. So you have to put some load over here to make sure that your location of the pole will not change. So that is what we call something kind of loading effect, and this has to be taken into account. This ZL has to be calculated separately and it will become a separate headache.
Understood, sir.
And why do you need to put the ZL? Because your pole locations, as you say, your pole location will change. So I have to put the ZL in such a way that neither the DC gain nor neither the pole location will change, even if I remove the R2 by R1 from the network.
Okay, sir.
Yeah.
And then like one more question, sir. Like they are given the phase margin of closed loop, no, sir. Actually, if we need to find the phase margin of closed loop, we need to find the transfer function as G by 1 plus GH.
Yeah, so that is a point. I guess those guys confused you by mentioning that statement in the question. Normally, the phase margin you never find for the closed loop system, because The whole point of calculating the phase margin was to not to put the system in the closed loop feedback, because analyzing the transfer functions of the closed loop systems become tougher and tougher as the order of the system increases, right? So we do the loop gain analysis first, then from there we calculate the transfer function without putting it in the feedback, then we do the phase margin analysis, and from the phase margin of the loop gain that we got, we then estimate if I put the system in the closed loop now, whether that system will be stable or not. So that's why we have not taken g upon 1 plus g, because it does not make sense to calculate the phase margin of g upon 1 plus g. I will directly check the step. If I know the transfer function of this, correct, I will directly apply the stability test on this now. Why to calculate the phase margin of this again? There is no point in doing this. So the way it usually works is we take the loop gain, calculate the phase margin, check the stability. Stability, how will you check? You just have to check the value of the phase margin. Phase margin has to be greater than or equal to 45 degree to ensure that your system will remain stable even if you put the system in the closed loop. So do not think that you have to calculate the phase margin of this particular transfer function. You have to always and always calculate the phase margin of loop gain, not for the closed loop system.
Okay, sir. Like if the phase margin of the both, where only g and g by 1 plus g will be same, or
the phase margin of g and g upon 1 plus g, no, how can they be same? They will be different, right? But what will you do after calculating the phase margin of g by 1 plus g? Because see, remember, I will just tell you, the way you usually do it is something like, let's say you have g, you have h, correct? You have, let's say, some system something like this, correct? Now the way loop gain is nothing but your g times h, correct? So you calculate the phase margin of this. Remember why did we first started doing this? Because the closed loop transfer function was g upon 1 plus gh. You agree with this or not?
yes, sir.
Correct. So we actually try to do everything, our analysis, around the point where gh becomes equal to -1, and that point was basically where our phase will hit 180 degree, correct? We just want to check that our g times h should not be greater than 1 at that particular point, or else our system will oscillate. So that's why we took the help of the Bode plot. We went to a point where our phase margin, not phase, our phase was, let's say, hitting 180 degree, correct? And then we calculated what is the phase that I have available. Even if I have some, let's say, 2-3 degree phase available, correct? Then I know that when I put this system in the feedback, then my system is stable. Now what you are telling me to do is basically, you are basically trying to calculate the phase margin of this, correct? So now what will you do after doing this? So it will look something like this. So I already have a system which is under a feedback, now, correct? Now what you are asking me to do, if I consider this as a separate system, separate block, now you want to include one more feedback going like this, correct? So this is what I was trying to say, like whatever analysis, the phase margin analysis you do it for the loop gain first, correct? If you do a phase margin analysis on this, what will this yield to you? It will just tell you whether this particular system, what is this system? You have two negative feedbacks now, one negative internal feedback and one external feedback that you have intentionally put to calculate, to check the stability of the system. Why? Because you are asking me to calculate the phase margin of the closed loop system. So if it comes out to be, let's say, 30 or 40 degree, then I can ensure that if I put this transfer function in the negative feedback, then this system will become stable. But am I checking the stability of this system or am I checking the stability of this system? It is still not clear.
Yes, sir. I'm clear. I am clear, sir. Basically, we are trying to check only the loop gain. By checking the loop gain, we are checking the stability of the closed loop only indirectly.
Yes, correct, exactly. So if you are checking the stability of the closed loop system itself, then it is as if you have intentionally put this negative feedback system into one more negative feedback, and that does not make any sense unless until you have some additional advantage of doing that, right?
Fine, sir.
Yeah, great. Okay, yeah, so that was a good doubt, and I guess we can move quickly with the next assignment because I have to give some resources at the end as well, right? So now we will try to cover this very quickly because this was the most important part. This is where students make a lot of mistake, calculation of the phase margin, zeros and the poles. So that is why it was necessary to cover this part in very much depth. So let's go with the assignment number 8 now. So now this was just a, if you look, this is the circuit that they have given. These are two simple topologies. We have already covered them in our live problem solving sessions. So what they have, let's just see what they have given. They have given the VDD, the VT, the mu n Cox, the mu p Cox, the lambda, the channel length modulation parameters, the minimum channel length, and the room temperature and the Boltzmann constant. Correct? Now they are also asking us to use this relation RDS is equal to 1 upon lambda ID if we want to calculate the R0 for a transistor which is not of a minimum length. How we can find out the lambda for transistor which is having, let's say, L of, let's say, 4 micrometer. Then to do that we have to use this relation lambda into L is constant, and this is what they have mentioned over here. Correct? So if you increase the channel length, your lambda will decrease proportionally. Correct? Now let's see what they have given. This is the first circuit that I have. You can see this is a source degenerated common source amplifier which is with a resistive load, and the second circuit is nothing but a common source amplifier with a active load. This is not a CMOS inverter, okay, because this is a biasing input. I am not applying Vin over here. Correct? Now what they have mentioned is they have given me the dimensions, they have also given me the current, they have given me the RS, they have given me the RD. So everything has been given in the question. Now they are asking me to calculate if the small signal voltage of 1 millivolt is applied, would determine the small signal current through M1. Correct? So now they are asking me to find out the relation I out is equal to, what is this relation? I out by, let's say, something I am applying V in. Correct? We know this relation, we have seen this so many times. This is nothing but the capital GM of the circuit. So indirectly they are asking me to calculate the capital GM of the circuit. Now remember, this is a source degenerated amplifier, so the capital GM of the circuit and the GM of this transistor will not be same. So we have already seen this, we have derived this multiple times. So the GM expression for this circuit is nothing but small gm upon 1 plus GMRS. The GM actually decreases, right? So the another way to think about this circuit is basically this is introducing some kind of feedback which will help to linearize the circuit. It will increase the linearity of the circuit at the cost of decreasing the gain. Correct? So now to get this, I know the value of RS. Do I know the value of GM? I don't know, but can I calculate it? Of course I can calculate, because W by L ratio has been given to me, even the ID has been given to me, even mu and Cox has been given to me. So I will find GM from here. I know the RS from here, so I can get the value of the capital GM from here. Correct? And my I out was nothing but GM times V in. Correct? GM is 1 millisiemens. The input that I had applied was 1 millivolt. Correct? So that I out that I got was 1 microampere. Correct? So this question is solved very easy. If I try to calculate the gain of the circuit, it will be nothing but the capital GM times R out. Capital GM is nothing but 1 millisiemens. The R out is nothing but equal to RD. The RD has been given in the question as 4 kilo ohms. Correct? So that's how I got the gain of the circuit as 4 volts per volt. Correct? So two very easy questions. Now coming to the third question. Again they have given the dimensions over here. Correct? The biasing current for the transistor is 2 milliampere. Correct? Now they are asking me to calculate the input referred thermal noise voltage squared density of the amplifier, that in nanovolt per square root hertz. Correct? So let's quickly do it. Remember, input is at a high impedance. Correct? So what we are usually do, any noisy circuit we represent it as what? Noiseless circuit. This is a 2-port that I had. Then I had some noise at input and I have some noise current source at the input. So using this model, I can completely remove all the noise from the circuit and represent it using the two source. Remember, when the input of the circuit has the infinite input impedance, this current source does not play any role. Only role that is played is by this particular voltage source. And how do we calculate it? Remember, we used to short circuit the output, correct? And we used to see how much current from each of these particular MOSFETs will appear at the output. Okay? Since this is grounded and even this is grounded for small signal analysis, the 4 kT gamma GM from M1 and M2 will both flow towards the V out, correct? And that is why I have added over here. Now what is the capital GM of this circuit? Can anyone quickly tell me what is the capital GM of this circuit?
Just GM1.
Yes, very good. So that is why I am doing what? To get the input referred thermal noise voltage, I have to divide the output short circuit current with the GM square of the circuit, and GM is nothing but the GM1 over here. Correct? So this entire expression will be divided by GM1 square, and this is the same thing that I have done over here. Gamma has been taken as around 2 by 3. So this is the expression that you got for the input referred noise voltage. But they are asking you to get this in terms of units of nanovolt per square root hertz. Correct? So since I have to take the square root, I have to basically take a square root on this particular quantity, and that is why you can see a square root term over here. Since the K is given to me, temperature is given to me, GM1 I can easily find out. Why? Because I know the expression, it is nothing but 2 times mu and Cox W by L times ID. ID has been given, W by L has been given, even mu and Cox has been given. Correct? So that's how you will be able to find GM1 and GM2. Correct? And from here you will be able to get the expression for Vn, that is the input referred noise voltage density in terms of nanovolt per root hertz. I hope this particular part is clear, and if you do the detailed calculations that I have done over here, you will get this particular final answer. Correct? Any doubts at this particular point? Okay, then I will be moving to the assignment number 9. If you guys have doubt, then please feel free to poke me. Correct? So now in this assignment, this was a question that they had given, and the one more addition they have done is basically they have inserted a capacitor in parallel with this RS over here. Correct? So the W by L has been given, the bias current of 0.5 milliampere is given, the value of CS, RS and RD has been given to me. Correct? So now let's first do some analysis on this circuit. Correct? So can anyone tell me whether there is any zero in this circuit or not? See, this is little bit tricky. You are not able to see any parallel paths from the input to output, but still there is a zero in the circuit. Can anyone explain me why?
There is one path through like the transistor itself, GM.
Huh? But there is
And
no
then there
CGD
is-
now. There is no CGD.
Capacitor short, short, and still output is non-zero.
Yes, excellent, very good. So what this guy said is, you guys remember this was one of the hints that I had given while doing the lecture number 5 or 6, I don't remember exactly. So for finding out the zeros, I mean how many, does there exist any zero in the circuit or not, I had given you one hint. How many caps you can short circuit, how many caps you can short circuit and still your V out will not be equal to 0. Correct? This is one of the hints that I given in the lecture. So if this capacitor, even if I short circuit, this will just become a common source amplifier. My output will still be there, it will still be a finite. Correct? So I definitely know 1 0 has to be present in the circuit, but that is just a short method to understand whether there is a 0 in the circuit or not. Now we have to look intuitively what is actually happening. So what is the expression for the V out? It is nothing but the GM of the circuit as a function of frequency and the R out as a function of the frequency. The GM is a function of the I out, the short circuit current itself. Correct? So now remember, if somehow at a particular frequency my short circuit output current becomes equal to 0, don't you think that my output becomes equal to 0 or not? What do you think? If at particular frequency, if my output, if somehow the capital GM of the circuit or the output, the short circuit current, if I present a short circuit at the output and calculate the current at a frequency, if this current becomes equal to 0, don't you think that the V out at that frequency becomes equal to 0? Are you able to understand? Guys,
Sir, I am not able to understand it.
yeah, so tell me what did you not get?
Like how exactly the zeros
Have you attended the live problem solving sessions that I had taken where I had told the method how to find the zeros and all?
I think they missed the particular session which you're talking about.
Okay, no problem. So just by looking at this expression, just tell me, see what is the zero of the circuit, what happens to the output at that particular frequency? It becomes zero, it is still finite. See, you are looking at this particular quantity, right? V out by V in at a particular frequency. What does the zero of the circuit means? The definition.
Output is zero.
Output is zero at that frequency, right? So
Yes,
this
sir.
is the output, the expression that I have written. Can I write the output expression of any circuit as the capital GM of the circuit into the effective output impedance of the circuit, both of them as a function of frequency?
Yes,
Can
sir.
I write them like that?
Yes, sir.
Right? Now the GM, the capital GM of the circuit, how did we find this? We short circuited the output, we applied a input and we found out how much current we were getting at the short circuit. We remember this?
Yes, sir. Yes, sir.
Yeah. So now I out, this I out by S, if I divide by V in, it will become nothing but GM of S. This is the GM that I had, right?
Yes, sir.
Correct? So this is the same expression that I have written over here. Correct? Now you inspect both these quantities separately. Correct? My V out is product of these two things. So I out is a function of S and even R out is a function of S. Now what am I saying? At a particular frequency S equal to 0, correct? If I out of S, the short circuit current becomes equal to 0, then what will happen to this particular term?
Zero.
0. If these terms become equal to 0, but if R out of S is not equal to infinity at that frequency, what is the product of these two product? What is the product of these
Zero,
two? 0. So did my V out become 0 at that frequency?
Yes, sir. Yes, sir. But how
Yes,
can we say I out is zero?
Yeah, so just remember. So I'm coming over there, don't worry. So I'm coming over there. So now remember, how can the I out become equal to 0? So remember, there is a source GM times VGS that is present over here, and this is connected like this. Correct? Now, if this point, if this particular quantity over here, if somehow, if this node becomes open circuited, so what do I mean is, let's say you have RD, you have VDD, correct? You have M1 over here, you have GMVGS, correct? And now this node is left floating. This node is left floating, and now I short circuit the output, correct? So now just tell me this GMVGS current that is there over here, correct? So now can any current flow out of this loop or it will not be able to flow?
There won't be any current out of
There
it.
won't be any current because it's an open circuit at the output. If some current flows at the output, then I have violated the KCL. Correct? Then I have violated the KCL. So now your only job is to find out, can this node become open circuited or not? Correct? So now
At
just
a particular frequency, the impedance will blow up to infinity.
exactly, excellent. And that frequency is this particular frequency. Do you agree with me or not?
Yes, sir. Got it. No. Thank
Yeah, got it. Excellent. So now that is why you have a zero in the circuit. So even if, so remember, having two parallel paths is a, what you can say, it is not the, what you can say, ultimate test of having the zero. If you have two parallel paths, there will be a zero. But if two parallel paths are not there, that doesn't mean there won't be any zero in the circuit. Are you getting this statement or not?
you. Yes, sir.
Yes, excellent. Now, if I want to find out the pole of the circuit, now how can I find out the pole? At the output, there is no capacitance. Only capacitance I am able to see is at this particular point. So the net capacitance is just CS. And now, if I want to, if I just give me a second. I guess I need to erase this because too much of khichdi has been made over here. Yeah. So now what I was saying is, so now what is the impedance looking up from here? What do you think? Impedance looking at the source of M1. Would it be
It's
something
just
like RD plus R naught upon 1 plus GM R naught, something like this? But
normal GM like degenerated by RD.
sorry.
RD
No,
will
I'm asking
act as
just looking up. See, remember, I want to find out the net impedance at this particular point, correct? So there is a RS looking down and there is a resistance looking up. So both these resistances have to be taken in parallel. Correct? Are you getting this or you're not getting this?
Sir, how like RD plus R naught by 1 plus G? How can we tell this intuitively without doing the small signal analysis?
Oh, I have taken an entire lecture on this. I took around something like 2 hours or 30 minutes and took a lot of circuits, and there were 4 or 5 circuits. There were basic 3 or 4 formulas that had asked students to just remember, and this is just one of them. If you can easily derive it, the only thing is if this RD becomes comparable to R naught, right? If this RD becomes comparable to R naught, then the impedance cannot be just treated as 1 by GM. This will be left as RD plus R naught upon 1 plus GM R naught. So you have to go back and refer that lecture. So that is why I have told in the problem solving sessions, please remember those expressions. Those are going to be extremely useful. They will help you a lot and save you a lot of time in the exam. So there were 4 or 5 expressions. You still have time. You can go back and remember those expressions before the exam. It will hardly take you 30 minutes. So this is one of the expressions. The only reason I can tell you why this expression is true is if you put R naught tending to infinity, then you can see that this impedance is becoming 1 by GM. So you remember, looking at the source of MOSFET, you get 1 by GM resistance. You remember this at least?
Yes, sir. Yes, sir.
Yeah, so that is the only reason I can give you why this expression is actually making sense to you. So that is the only reason I can give you right now. Otherwise, there is, just by looking intuitively, it is absolutely not possible to write this expression. There are 3-4 expressions that you have to remember. There is no other option.
Fine, sir. I'll go back and refer.
Yeah, please. Yeah, no problem. So we calculated the pole, we calculated the 0. So that's why this 1 by GM parallel RS came over here. So this is the expression of the pole. This is the expression of the 0. Now let's see what they are asking in the question. So first thing they are asking is the small signal voltage gain of the amplifier at very high frequencies. At very high frequencies, this capacitor will act as a short circuit. It will short the RS, correct? So it will be left as a common source amplifier. So the gain of the circuit is nothing but GM times RD, correct? So you can easily find out the value. Now basically what they are asking is, assume that the current in the transistor M1 is now increased to 2 milliampere to try to increase the gain. Determine the new position of the pole in the expression. Remember, this was the pole of the circuit, 1 plus GM-RS upon RS into CS. Now remember, what is the expression for the GM? Root of 2 mu n Cox W by L times ID. If my ID changes for the same W by L, correct, my GM will also change. If the GM changes, then my pole location also changes, correct? So that is why you have to find out the new pole location using this particular formula. Now come to this question. With current in the transistor M1 of 2 milliampere, determine the new position of the 0. What is the 0 that we had found out? It was nothing but 1 by RSCS, correct? So remember, the location of 0 will not change and it is not dependent on the GM, correct? So even if you do anything, burn more current, decrease the current, it is not going to do anything. The 0 expression will remain as it is and it will not change. It is not a function of the current that you are using to bias your circuit, correct? So now once this is done, the next question they are asking us is to calculate the Rout and the AV, the small signal gain and the output impedance at low and higher frequencies, correct? So now let me make this circuit for small frequencies at very low frequencies. The capacitor will act as an open circuit. Now what is this configuration? We have seen this multiple times. This is a cascade amplifier. So what is the Rout? Rout is nothing but RDS of this plus RDS of this plus GM2 into RDS2 into RDS1, correct? And what is the GM of the circuit? No, the GM, the capital GM is nothing but the GM1, correct? So the total gain will be nothing but the product of these two, and that's how you can easily get the final voltage gain of the circuit at low frequencies. Now if I make the high frequency circuit, I have to short this capacitor, right? That is why I have shorted the capacitor over here, and what you can see over here is that this circuit is now actually shorting the drain of this particular transistor itself. So the R out will be nothing but, since this terminal is connected to the ground, R out will be nothing but the RDS2 of this transistor itself, correct? It will be RDS2 of this transistor, and the capital GM, even if I short circuit my output, I just want to see how much of the current is coming over here, correct? Remember for this particular MOSFET, I have GM times Vin over here, and now I am doing what? I am short circuiting over here itself. Why? Because there was a capacitor and I have to short circuit it. So all the current will flow through this short circuit, correct? None of the current will go through here, because I am looking up, I have some finite impedance, and over here no impedance is present. So even if I short circuit the output, no current actually flows over here. So that's why the GM, the capital GM of this circuit is 0, correct? And that's why your net gain of the voltage gain of the circuit is also 0. Okay, I hope that particular point is clear. Now I will just move on, just see if I have some important sums to cover, because we don't have a lot of time to cover a lot of things. I will just get important questions out of this assignment. So now, okay, I need to do this. This is little bit important. So all the VDD, VTH, mu and Cox values have been given to you, and the W/L ratios have been also given to you, correct? So now they are asking us to calculate the output resistance. We already know what is this. It is nothing but RO4 parallel RO2. We have done this 100 times. Now how can you calculate RO4? It is nothing but 1 by lambda ID, correct? And what is ID? ID is nothing but the current that is flowing through MOSFET 4, and this is nothing but I0 by 2. Please remember this. Do not buy the current flowing through this M4 is I0 by 2. Okay. So while doing the calculations, please use this value of current and do not use the value of I0 over here. Correct. So now the next they are asking is to calculate the input referred noise voltage density. Okay. So this is going to be a little bit important. So now what happens with the M0? What happens with the M0? So whatever current the 4 kT gamma GM is there, correct? It just acts as a common mode signal, right? So whatever signal I inject from here, the same signal is gonna appear, the current, this noise current will get replicated over here and it will appear over here. The same current now will get, it will also go through the M2. So basically what you can see, this current is actually getting divided by 2 and then it is getting replicated to M1 and then M2. The M3 current mirror replicates this current into the right half branch. The current, the division that has happened between M1 and M2, so the current also flows like this and the replicated current flows like this, correct? Since the same current, this is let's say this is 4 kT gamma GM0, let's say by factor, some division factor by 4. Why by 4 factor? Because not by 4 factor, let me just think about it. Let's say some factor x, because some current division has happened between both of them, right? If I put a current, some current like this, some current will go through here, some current will go through here. Since both the stages are identical looking up, correct? What you can see over here, the current division will happen equal, and now this noise current will exactly get replicated on the top of V out, and the same current is exactly present at the bottom of the V out. So even if you short the output over here, no current will flow through the short circuit. So M0 does not contribute anything. The M1 and M2, the current you will directly get whatever input referred current, input referred noise voltage you usually get, right? Something like 4 kT gamma by GM plus 4 kT gamma by GM, correct? This will come from M1 and M2. We have seen this a lot of times. And now what about M3 and M4? So if you remember, for M4, if I have a current source which represents something like this current directly flows at the output, correct? So this current from M4 and M3 actually directly appears at the output. You just have to divide it by the GM of the circuit. So the current from M4 at the output will be nothing but 4 kT gamma times GM3, current GM4. The current from the M3 will also be the same. So that's why I have multiplied by the factor of 2. So the short circuit current at the output will be nothing but 8 kT gamma GM1 plus GM3. Why 8 kT gamma? Because of the combinations from the M2 and the M1. Remember, for a single-ended circuit, this would have been just 4 kT gamma. But since we have differential, it is 8 kT gamma. Correct? Now I have to divide it by the GM of the circuit. So if I divide this by the GM1 square, then you will get the final expression, which will look something like this. Correct? Now you just have to substitute the values, you will get the final answer. So now one more thing left is, I have already done this a lot of times, the ICMR, the minimum input range and the maximum input range. So the minimum input range is determined by the M0 going into the triode, the maximum is determined by the M1 going into the triode. Why? Because this voltage is fixed. Correct? So if you want to look, then please go through the whatever equations I have written, you will get how the ICMR and the OCMR has been calculated. Correct? I will just skip through it because I literally don't have any time. How will you calculate the unity gain frequency, the loop gain frequency? So remember, this is the final circuit that I have. I have to break the loop and then I have to do the exact same analysis that I have been doing a lot of times. Correct? There is a CL that is present. The dominant pole will be created at this particular location because apart from CL there is no other parasitic capacitance that is present. Correct? So the unity gain bandwidth is nothing but the DC gain into the dominant pole. DC gain I already know now. It is nothing but GM1 times this R02 parallel R04, which I have already taken, and the pole, the dominant pole, will be nothing but the 1 upon CL into whatever output impedance I see over here, that is R02 parallel R04. So if you multiply both of them, the unity gain bandwidth will comes out to be around GM1 by CL, and it is no wonder why this expression comes again and again in each and every assignment question. Correct? So now once this is clear, they are asking us to determine the approximate 3 dB bandwidth of the closed loop amplifier. We have already seen how to do this, right? We just multiply by 1 plus A beta and we find out that it will usually come out to be omega UGB only. So if you know omega UGB, then this is usually equal to the 3 dB bandwidth of your closed loop amplifier. Correct? And why does this happen? Because I will just give you a quick hint. Let's say this is a single pole amplifier. Correct? Now I have reduced the gain. See, this is a unity gain amplifier, right? So for the closed loop, let me just change the color of the pen. Yeah. So for the closed loop, since my gain is 1, right? So that is 0 dB. So I have shifted this plot from here to here. Correct? So I will hit here and then my roll off will start. So what you can see over here is that your omega UGB is equal to the 3 dB bandwidth of the closed loop system. Correct? See, this particular slant line cannot change. Correct? If you make the open loop system, if you put a feedback, this particular slant line has to be respected because there is only one pole in the system. Correct? So now if you reduce from ADC to 0 dB, this is where you will hit the slant line and this is where you will continue. So that's why your omega UGB became equal to the 3 dB bandwidth of the closed loop system. Okay? Now once this is done, let me just see if I have something important to cover, or else I will just skip. This is easy, we have already covered this. By the way, if you guys have any doubts on this, I have taken a complete design example. Okay, this design example will make this circuit even more clear. It will give you a lot of intuition how this circuit is even designed. Okay, so if you have to do any analysis on this circuit, please go back and refer week 11 lecture that I had taken, the week 11 problem solving session. Okay, unfortunately I don't have any time to cover this particular circuit right now because I have to cover a few more sums and I have to give you a resources and what you have to prepare for cracking the interviews. Okay, so I have to skip this unfortunately. For the assignment number 12, for this particular circuit also, this circuit was completely covered and the design example was also taken on this. So design example, if you look, week 12 problem solving session. Correct? Please go back and refer to this week 12 problem solving session. If you guys want to solve any questions, if you don't understand any particular thing, let me just check if I can help you and solve any particular sum in this particular problem. That is the assignment number 12. So the getting the DC gain is not a problem. This expression is known, it is very trivial. You can get the GMs and the R0s from the circuit. So the gain of the circuit is around 104 dB. Let me just check whether calculating the unity gain frequency is going to be difficult. Again, it is not going to be difficult, right? The unity gain frequency is very easy. Again, it will come out to be same, GM1 by CC. Correct? Now let me just see if I have made This is a transfer function that you have, that you will get. There will be 1 0 because of the Miller compensation. There are going to be two poles. One dominant pole will be there at the output of the first stage, and then there will be a second pole at the output of the second stage. Correct? Now you can easily find out all the things. The omega UGP, the 0. This sum is not gonna cause a lot of problem. Yeah, so this sum had nothing. I mean, there is no trick that is involved in this particular question. This question could have made even more difficult by introducing a series nulling resistance or by doing some crazy things, correct? But fortunately, the question has not asked you to do things like that. So please go through this particular slide. I have already solved this question over here. Also, the solution for this problem has also been uploaded by the TA. So please go through both these documents and please complete this. And if you still have doubts, then I will refer you to this. Please go through the week 12 problem solving session and understand how this circuit has been designed. It will make a lot of things much clearer. Okay, so now once this thing is clear, now let's move on to the most important part. I will just take maybe 6 or 7 more minutes, then we can go and enjoy our rest of the evening. So now, what are the additional courses after doing this course? What is the future path? What you need to do to become good circuit designer? So this course is not the last course that of the analog circuit design. This is just, I can say, this is just the second course. This is just one of the second course that analog people do. What is the first course? The first course is of course your analog electronics that you study, right, in your second year. So this is the second course. This is where you are standing. This is the analog IC design. Now to become good circuit designer, now this is not enough, correct? Because world is becoming competitive. If your job gets completely automated, you will be out of the job, correct? So now the jobs are only going to become tougher and tougher, and so you have to make sure that you have the skill set where you can't be replaced by the company. So now what are the other courses that you can do? So first I will recommend that if you have not done the digital IC design course, then please do that. I will also tell you which course you need to do. After that, you can do this power management IC course. This course will teach you the design of band gap reference circuits. It will also teach you the design of the LDO, the low dropout linear regulators. It will also teach you the design of switching regulators. Remember, automotive market is booming right now. There is a complete division in the Texas Instrument which designs the regulator for automotive applications, correct? They have the PMICs that have been designed for that particular purpose, correct? So these three things, the band gap reference, the LDO and the switching regulators, you will be able to get from this particular course, the power management integrated circuits. The next thing that you can do is the phase lock loops, correct? Now these courses, apart from the digital IC design, please do these courses only if you have a clear-cut understanding of what you have studied in this course. Please do not have a half-baked knowledge and directly jump onto this course. These courses are difficult. These are advanced courses. Okay, unless and until you have absolute clarity in this, please do not expect that you will understand most of the concepts from these courses. The phase lock loop course, it will teach you how to design the oscillators. Correct? I talked about the LT. Correct? The 900 megahertz band. Who designs this? How does your mobile generate this frequency? It is generated by a block called as a PLL. Your processor, correct? Your processor, the latest Apple processor has 19 billion transistor. Now for that processor you need a clock. Who generates this clock? Again the phase lock loop blocks generates this clock. Correct? So there is a serial link that goes on. That is, if you have a processor on one hand, correct? I guess I have an image. Let me just pull out that image. That will be much better. Oh, sorry. Yeah. So this is the image that I was talking about. Just give me a second. I have taken this from LinkedIn. One of the CEOs of some Fortune 500 companies had posted this image. Yeah. So what I was trying to say over here, if you look, this is a GPU, correct? This is a GPU that you have, and this is where you have a memory, correct? If you remember your von Neumann architecture, then this processor and memory have to keep in touch with each other. In each and every processing cycle, some data is fetched from the memory, the processing is done, and again some data is fetched back into this memory, correct? So now there is a interface, right? There is a data that has to be transferred from processor to memory. Correct? Now, and that has to have operate, and this has to happen at very very high frequencies. To synchronize this operation also I need a clock. Correct? So now how who generates this clock? Again your phase lock loop generates this clock. Correct? So now this is the importance of the phase lock loop. Correct? So now once this thing is clear, now another domain is the mixed signal circuits. This is where your ADCs and digital to analog converters come into the picture. You have all studied ADCs and DSCs in your basic course, but now we want to dive deep into the transistor level design details of these ADCs and DSCs. Correct? And remember what is the foundation of designing all these circuits? The last lecture, so week 12, so sir had shown you some plots, GMRDS, then FT and all, correct? So whatever plots he had shown you and all, so that forms a basis, that forms a tool for analog circuit designer. That's from a tool for analog circuit designer. So remember those curves that sir had taught about, the intrinsic gain of the transistor, the FT, how the VDSAT varies with the VGS minus VTH and all. So those particular curves are not only useful for this course. If I tell you to design a current steering DAC, that is a digital to analog converter or flash ADC, or some circuits like this, you would have to go through those plots. Unless until you have these plots characterized for that particular technology node, it will become very very hard to design the ADCs, DSCs, or even the phase lock loop circuits, the charge pumps, the frequency divider and all. This is what I am talking about. Correct? So please make sure that you study the week 12 that particular lecture, the transistor summary lecture, to such a depth that you don't have any doubt left over there. Correct? If you still have doubt, please go to the internet and study about GM by ID design. Correct? Please have a clear cut understanding of this. At least I want you to get a feel of few numbers like GMRDS and the FT. Okay, unless until you get a feel for these numbers, it will become very difficult to design good circuits. Okay, so now these are the courses, these are all the courses, and now which market is booming right now in the world of the semiconductors? You can say this particular market, for example, this high speed serial links, correct? The circuits for the data centers have seen exponentially growing demand, and you know which company I am talking about. Can you give me a hint which company I am talking about? Which company? Sorry?
Texas Instruments.
Not Texas Instrument. Does Texas Instrument doesn't design the processors for the data center? Intel is there. Okay, Intel is good. But right now, one company's share price has gone crazy in last few months.
NVIDIA.
Exactly, NVIDIA. Yeah, and why the demand of the NVIDIA has gone up? Because of the generative AI and all. And why are we looking at the generative AI, the transformers? Because of the chat GPT. So the chat GPT is based on the transformer model. So the transformer model, the way, if you look at the structure of the transformer models, right, it is nothing but the complete matrix multiplication. A very big matrix, something like 10 lakh cross 10 lakh matrix multiplications and all, correct? So these matrix multiplications can easily be parallelized, right? And GPUs basically overperform the CPUs when you want to do the operations in the parallel, correct? And where does all these operations happen? Inside the data center. So that's why the demand for the NVIDIA's GPUs inside the data center has gone up. And remember, I have to transfer a lot of data within the data center itself, and these high speed serial links that you are seeing over here, I will just tell you rough number at what data rate this communication is happening. So the data rate is around 114 Gbps. Just imagine this. This is I am talking about the data. I am talking about the optical fiber, the data rate that happens over there. If you talk about the electrical data rate on the copper, correct? It will be something like between 20 to 40 Gbps. Just to give you an analogy, remember in the 5G, the data rate that we are targeting, the peak, the maximum data rate that we can get is 1 Gbps. This is at least 20 or 40 times higher than that. Correct? Now, how can you design the circuits which can work at such a high frequency? This is one more challenge, right? So, unless until you have an analysis, unless until you have a good intuitive understanding of the 3 dB bandwidth and the gain bandwidth product of the circuit, that is the unity gain bandwidth of the circuit. And unless until you know what this FT parameter is, you can never design these circuits. These are the state of the art data, these are the state of the art circuits, right? And this is a state of the art field. It is so state of the art that 2 of the people who have done PhD in our groups, who had done their PhDs in the RF circuits, they have been pulled by the company into this particular field. They had worked on the RF circuits, but still they were pulled into this particular job. Why? Because the amount of money that has been poured into, amount of investments that are going into in this domain are exponentially increasing. Those are crazy. They are going huge. Remember, the recession is happening, correct? The recession impact was seen on the US, but the investments on the generative AI, on the data center, those particular industry did not see any impact of the recession. The investment still kept going higher and higher, and I don't think this particular thing is gonna stop for at least 4 or 5 years, correct? So now once this thing is clear, radio frequency integrated circuits, this is optional. I will leave it up to you whether you want to go and design the circuits at 28 gigahertz, 5G, 6G and all. I won't force you to go and look at the courses over here, but at least make sure that the phase lock loop, the power management ICs and this high speed serial link you do, because this particular course will add a strong point on your resume that many people usually don't have this course on their resume. And the reason for this is only one thing: nobody apart from IIT Madras and somewhat IIT Kanpur, nobody teaches this course in the entire India. That is the problem, correct? So but the thing is, some resources are available online. I will just tell you. So now once I have told you what courses you should do, let's have a look at the resources. So first start with the field which is booming right now, the high speed serial links. So there is a Professor Elad Alan from UC Berkeley. He has uploaded the lectures on YouTube. So please go through this lecture series and understand how these serial links are working. One more lecture series is by Professor Nagendra Krishnapira, and he has also uploaded this on YouTube. It is named as VLSI Broadband Communication Circuits. Why broadband communication circuits? Because I told you the data rates, right? I told you the data rates, the 20 and 40 Gbps. These are not very small data rates. So that is why we are calling it as a broadband communication circuits. So first you can do this lecture series, and then on addition you can do this lecture series as well. Correct? Now apart from this, for power management circuits, there is a course available on the NPTEL by Professor Kadir Khan. So please do this course. The only thing is, this course you will feel very heavy if you don't have enough background on control systems, correct, and analog IC. So please make sure that you completely nail both of these, at least Bode plot, Nyquist plot, and the understanding of the unity gain bandwidth and all, correct? Unless and until these two things are, these few topics are clear, please do not jump onto this course. You will scratch your head for 1 year. Okay. Now one more thing, for the phase lock loop, there is a course available by Professor from IIT Madras, Professor Saurabh Saxena. Again the same thing, before jumping onto this course, please make sure your analog IC design basics are completely clear. Okay, and if you want to refer a book for this, then the book you can refer, Professor Razavi has written a book, entire book on the PLL. So you can search it on the Amazon. The book costs a lot, but it will be worth. Please see if you can get this book somehow. That book is a great supplement for this particular course. Correct. One more book I remember is Gartner. So you can read this book while studying this course. This will make your fundamentals even stronger. Now for mixed signal circuits, you can study this course by Professor Shanti Pawan. And there has been recently some playlist has been uploaded from IIT Kanpur. So there is a group from IIT Kanpur, the Solid State Circuit Design Group. They have their YouTube channel. You can go and see what kind of lectures they are uploading. Most of their students are professors of Shanti Pawan only. So I can at least vouch for them that they are teaching brilliantly. The way they teach it has a lot of similarity with how the Professor Shanti Pawan and Professor Nagendra Krishnapura teaches. Correct? So you can go back to this playlist, and you can also refer to some of the lectures of their mixed signal IC designs. Okay. Now coming to the digital IC design course. So there is a professor from IIT Madras called as Professor Janaki Raman. So if you want to understand the transistor level design of the processor or the multipliers and accumulators, how to design the multipliers, the transistor level circuits I am talking about, how to size the transistors and all, and how to make sure that the setup and hold time, the violation, the static timing analysis is made for those particular things. This course is one of the best that you can get, even compared to the foreign university lectures that have been uploaded. The way Professor Janki Raman teaches is very famous for his teaching style. So I will just recommend that please go through this particular lecture series. Apart from this, if you want to go to the radio frequency integrated circuits, then you have to go to the ICS website. So there is an integrated circuit systems group from IIT Madras. So from there you have to go to this teaching tab. Once you go to this teaching tab, correct, you will see a lecture by this RFIC, the radio frequency integrated circuits by Professor Sankaran Aniruddhan. These are all the lectures that you will be able to see. So this course will teach you how to design the low noise amplifiers, the power amplifiers, the mixers and all, correct. So this course, if you want to make your career in designing the circuits for 5G, 6G or for radars, I am talking about radars which are operating at 110 gigahertz and all, correct. So this course will form as a basis. This is just form as a basis to make sure that you have a required background to jump and design the circuits for 5G and 6G. Remember, 5G has two bands. One is sub 6 gigahertz and another is at around 28 gigahertz. Some band is also there at around 39 gigahertz as well. So designing circuits at 28 and 39 gigahertz, it is little bit challenging, right? So designing millimeter wave circuits, this course will not teach you, but definitely designing sub 6 gigahertz, the course will definitely help you to nail this particular domain, correct? Once this is clear, let's look at what projects you can do after doing this course. So the first and obvious project that you should definitely jump after your exams is design of two-stage op-amp. Remember, I have covered at least 5 or 6 design examples in my live problem solving sessions. So I would recommend you go to the week 12 lecture. I have literally calculated W by L ratios of the transistors as well, correct? So now you go to the week 12 lecture, you implement the topology that I had implemented in the cadence directly, correct? And now after that start tweaking the parameters. Unless until you do the tweaking, you won't get a feel. But remember, the way the circuit designer actually designs, I am talking about the professional circuit designer. So let's say you have been given 15 days to design a two-stage op-amps for a let's say low dropout regulator, correct? That low dropout regulator has a two-stage op-amp inbuilt in it, correct? So your boss gave you 15 days. So now amateur circuit designer, when I was in my first year or first or second year, how I used to design the circuit? So it was something like 3 days to understand the theory, and then 12 days I used to play on the simulator. But right now I will tell you how my design method has evolved over the time as I gained a lot of experience, correct? So the more professional way which I usually think, and I have seen people designing, so usually it is something like 10 to 12 days of theory and now just 3 days of execution, that's it. Understand the concept, understand the circuit in such a depth that you know if my simulation doesn't give you a proper result, you will immediately have in your head what I need to do next if this answer doesn't come in that particular manner, correct? That is the level of expertise that I want you to get for each and every circuit, correct? And if you mention this project on your resume, correct, and if you can't explain to the interviewer how you have designed the circuit, how you have tweaked the parameters, trust me, your interviewer will make sure that he will make a grill sandwich out of you. Okay, he will grill you in an oven. So you have to make sure that your theoretical understanding is up to mark of what these companies expect in the interview. Okay, once this is done, then you can also do an active filter design. So whatever two-stage op-amp you have designed, so you can also put some RC network around it and you can design a high-pass, band-pass or low-pass filter circuits. The next projects from the after doing the PMIC course will be of course design of a low dropout regulator and the design of the band gap reference circuit. So how can I generate a voltage of 1.2 volt in my circuit which will not vary even if I vary the temperature of my mobile, let's say from minus 20 degrees Celsius to let's say 60 degrees Celsius. Correct? I need a circuit which will give me a constant voltage independent of the temperature. So this is where the band gap reference circuits comes into the picture. After doing the PLL, you can design the voltage control oscillator, the phase frequency detector, charge pumps, as well as the frequency dividers. I don't want to go into the details of this. After doing the SERDES, correct, you can design a equalizer circuit, and after doing the courses you will understand how you can make a circuit which can compensate for the channel loss. The channel loss means you have a processor, you have a memory, the interface between them, correct, it acts as a transmission line at a higher and higher frequencies, correct. So it has a frequency dependent attenuation. So now how can I introduce a frequency dependent gain in my circuit so that this gain multiplied by the loss, the frequency dependent loss, will give me some kind of flat response like this, correct. So that is where your equalizers comes into the picture. After doing the RFIC, you can design low noise amplifiers, power amplifiers, and the IQ modulators. So these are all the projects that I want to list. The important projects that you can do that you should do if you want to target the analog design job in the industry is two-stage op-amp, this active filter, the low dropout, and this band gap. At least these are the 4 projects that you will see on the resume of each and every MTech guy who is doing the MTech in old IITs and the IISc. So I want you guys to compete with them. I want you guys to don't fall behind them. I want you guys to give them a tough competition, correct. And right now so many resources are available on the YouTube and on the LinkedIn. Without help of anyone, you can definitely do at least these 4 projects. Okay, the only thing that you need is a cadence, that's it. Correct, let me see. So these are the topics that they usually ask in the interview. The first one is the RC and RL circuits. By the way, let me just give a standard disclaimer. I don't have any tie-ups with any of the YouTube channel, and neither the NPTEL has. Okay, these are the purely recommendation out of my experience, and NPTEL does not recommend any of these channels. So they will first grill you on the RC and RL circuits. They will ask you to determine zeros. They will ask you to determine the poles. They will ask you to basically write the impulse response. They will ask you to write the step response of the RC RL circuit, determine the order, the first order, second order, and they will keep on doing the crazy combinations. They usually take up to 12 or 15 circuits during the interview, and they expect you to write the expressions or write the curves, how the output response of the RC circuit will look like. So I will just give you one example. If you have R over here, if you have C over here, correct, and if I just put a capacitor like this over here, this is V out, this is Vn. We have solved this type of questions in the problem solving sessions, right? So they will ask you, just by looking at the circuit, tell me the poles, tell me the zeros, draw the step response of the circuit, tell me the slope of the step response at t equal to 0. So these are the few common questions that you will encounter in each and every interview. So, and where should you study this? So remember, there are 2 very good channels. One is Himanshu Agarwal. He's a engineer. He's a analog engineer at Texas Instruments. Another is a Chambian T. He actually retired from the BITS. I mean, he take the voluntary leave from there. He was an engineer at Silicon Labs, and he did his masters from the IIT Madras under Professor Nagendra Krishnapura. So now in those channels you will see a lot of questions like this. So now I would request you to please go through those lectures, completely understand how they are solving this type of questions, and then go to IIT Madras website that I told you, the Integrated Circuits and Systems group. There you will, in the assignment section, you will find a lot of questions like this. Once you have understood the theory from Chambian and Himanshu Agarwal's lectures, and apart from the questions that I had solved in the problem solving sessions, then go and solve these the questions that have been given in the IIT Madras assignment. Once you do that, then I can guarantee you that no interviewer can trouble you in the RC and RL circuits. The next favorite questions in the written test are op-amp plus MOSFET questions. So you can find this question on this particular channel, the Himanshu Agarwal's YouTube channel. Over there you will see a lot of tough questions from IIT Madras interviews, the written test as well as the TI written test. He has taken some good questions from there, and then he has solved those questions and made the video of them, correct? So please refer those things. The differential amplifier, the 2-stage op-amps, whatever you have covered in this course, I can guarantee you that this is more than sufficient for cracking any interview. For band gap reference, I will heavily suggest you please go through the PMIC course by Professor Kadir Khan, and there is one more YouTube channel called as a Hafiz KT. So he has designed the band gap reference. He has designed the band gap reference and he has also simulated in the cadence as well. Correct? So you can go and replicate this circuit first, and then maybe you can design your own band gap reference circuit. Correct? And the next thing is the low dropout regulator. Of course, you have to study the PMIC course, at least the first half of the course, to understand how does this low dropout regulator works. Correct? So these are all the topics that I wanted to cover. Now one more thing, if some of you want to go into the research domain and want to read few research articles, I will just suggest one source, since I assume most of you are from the BTech or maybe MTech from the, let's say, state colleges. So there are some magazine articles called as Solid State Circuit magazine articles. Correct? I will recommend only two authors first. First is of course legendary Professor Razavi, and second is Professor Ali Sheikhul Islami. He is a professor at University of Toronto, Canada. So these two guys write a very deep intuitive articles in this Solid State Circuit magazine. So instead of scrolling your time on the Netflix or something, if you really want to do some good research, I will recommend you that please look at the articles that are written by these two professors, and they will change the way you look at the circuit. Just like after doing this course, you can now at least tell me what is the output impedance, the input impedance, what are the poles and zeros just by looking at the circuit. So this course has done that job, right? So similarly, if you want to go more deep into the intuition, you have to read the articles which are written by these two professors. You have to go to the Solid State Circuits magazine first, and there you will see a lot of articles which are written by these two professors. Okay, so that is how I will recommend if someone wants to do a research. That is how you should first strengthen your grip, and then you can actually jump onto the research papers to do whatever research you want. So okay guys, so this diagram I had just taken to explain the SERDES. There is nothing I want to mention in this particular diagram. So this is the all thing that I wanted to cover. I know I was not able to cover assignment 11 or 12 up to such a great depth, but I have already covered whatever I wanted to cover. The pole frequency, the pole analysis, the unity loop gain analysis, whatever I have to give, I have already given. I just want you guys not to judge yourself by whatever marks you will get in the exam. The exams you will get just a certificate from it, but the way people will judge you after doing this course is from all these concepts that are listed on this particular page, right? All these concepts that are listed in this particular page, people will ask you questions on that. Hey, tell me what have you learned from this course? Can you tell me how the two-stage op-amp is designed? How you design the second stage of the first stage amplifier? How you will design the second stage of a two-stage op-amp? Why I have to keep GM2 at least 10 times of GM1 in the two-stage op-amp? What is the reason of doing this? How to improve the phase margin if you are not getting the phase margin in the simulator? So let's say you go to the industry after 4 or 5 years, you will have juniors working under you, correct? So they will definitely get stuck during the simulations. So you should have the enough theoretical background to guide them and to solve their problems. So this is how people are gonna judge you. They will not judge you whether you have a certificate from the NPTEL or not. Having the certificate will strengthen you. It just tells you that you have the skill. But to make sure that you really make an impact, you have to make sure that you do a lot of projects, and for the projects you ensure that you have a sufficient theoretical understanding. You have to reach up to a stage where you will spend 80% of the time on the theory and then 20% of the time on execution. Correct? So remember, what is the job of a professional painter? He has trained 15 years just to draw your face, right? If I ask him to draw your face, you are seeing the videos on the YouTube where the one guy will be there. He will sketch the people who are sitting in front of him in the metro. He draws them within 10 minutes. Correct? Remember, he has trained for this for 15 years. Correct? 10 or 15 years of life he has spent, and within 10 minutes he was able to produce such a classical art. That is the job of the analog designer, right? That is the amount with which you have to familiar yourself the theoretical content, so that the execution time will be just 20 or 30%, and the theoretical part you have to spend most of your time understanding it. Correct? This is I'm talking at least at the first level. Once you go to the industry, this equation will change completely, because the requirements will be completely different over there, and to meet the specifications you have to done a rigorous simulations. Okay, so that's it from my side. If you guys have any doubts, this will be a good time. I will be happy to interact with you. This was whatever I can give within 2 or 3 hours I have already given. If something has not been given from my side, if you feel upset about some particular part, I'm really sorry if I was not able to cover that, but please feel free to drop the comments in the YouTube community section. If you still have any doubts, please feel free to poke me on LinkedIn. I will be happy to help you over there. So thanks a lot, guys. Any comments on this? Were you able to enjoy the course, or it went above your head?
Sir, really thank you so much, sir. Like all your efforts, they are so good, and you took this much efforts to give resources and all. It's so good. Thank you.
Thanks,
sir.
man. I really appreciate that.
The course generally was a bit tough, sir. Like I need to put so much efforts. I'm right now in my 3rd year, so in my BTech. So I need to put a lot of efforts, but it's good. The efforts are worth it, sir. Now I can like feel the experience with among my peers. I have like good knowledge on analog electronics, so that's good.
Yeah, and see, don't get disheartened. This subject demands a lot of effort. I will just tell you one thing. I had started doing this exactly in the 3rd year. For those 6 months, when I was doing the NPTEL course, I had done the course of Professor Shauri Chatterjee. So for those 6 months, I left all other subjects and I just focused for 6 months only on that subject. This subject demands a lot of intuition, lot of hard work, and that's why not a lot of people are going to the analog side. So that is the advantage for you, because not a lot of people can compete with you if you have a good amount of knowledge on this. If you get a grasp, if you get a good hold on this, then just trust me, the amount of experience, the level of your expertise after 10 years, it will be on a completely different level. You will laugh at yourself. If you go into the company after 5 or 6 years, you will laugh at yourself like what you were when you were in the 3rd year of your BTech. So that is the amount of expertise that you will get if you spend a lot of time on this thing. The only thing is, this field is tough, demands a lot of hard work and intuition, but that's okay. If other people are not able to do it, industry is paying you well, we are the people who do it, right?
Yeah, sir. Thank you so much for all your effort. Thank you.
Thanks a lot, guys. What about the other guy? Were you able to enjoy the course? Yes, I guess. Yeah, okay, you're good. Okay. I guess you put some comments. Thank you. You have given great content. Thank you. Okay, thanks a lot, man. I really appreciate it. Yeah. Okay, guys, I guess then we are good to go. Thanks a lot for staying here for almost around 3 hours. All the best for your exams. Nail the exams, and please keep in touch with me. I will be there on LinkedIn if you need any help. Thanks a lot. Take care. Bye bye.
Thank you so much, sir. Thank you so much.
Thank you, sir. Thank you. Bye bye.